Good evening, and welcome to the Sleepy Geographer. I'm glad you're here. Wherever you are, whether you've just turned off the lights or you're drifting beneath a blanket of night sounds, this is your moment to unwind, to let the world slow down a little. Tonight, we're setting out toward the edges of human understanding, to the places where the maps once faded into sea monsters and imagination, and where, even now, vast corners of our planet remain hidden beneath cloud, ice, and ocean. This is a quiet journey to where the map ends. Before we begin, I'd love to know where you're listening from. What corner of the world is your bedtime landscape tonight? It's always fascinating to see how many latitudes this little community stretches across. And if you enjoy falling asleep to geography's softer side, please do give the video a like and subscribe so you don't miss future journeys. A heartfelt thank you to everyone who's already joined this calm expedition. It truly means a lot. I do hope this video isn't too interesting that it keeps you awake. But if it does, at least you'll drift into tomorrow knowing a little more about the mysterious edges of our world. So, where exactly does the map end, and what lies in the spaces beyond the ink? For as long as humans have drawn lines, we've wondered what lies beyond them. The first maps were not attempts to master the world, but to make sense of it, to give shape to mystery. On scraps of leather or pressed clay, the known world sat like a small island surrounded by uncertainty. Oceans stretched endlessly. Mountains guarded the horizon like folded secrets. Picture an ancient cartographer, hunched by lamplight, feather pen trembling slightly as he reaches the boundary of what anyone has seen. His map is a confession as much as it is a record. Here, the world fades. Centuries later, a research vessel hums through dark waves, its sonar painting unseen ridges thousands of meters below. The glow of the computer screen is the new candlelight. The tools are different, but the feeling is the same. Curiosity pushing against the edges of the possible. To live on a mapped planet might seem comforting, but in truth, our knowledge is patchwork. We have better maps of Mars than of our own seafloor. Vast caves twist beneath us, uncharted. Forest canopies still hide entire ecosystems. Even the air above, shifting and alive, holds patterns our instruments only partly grasp. In this journey, we'll trace the many frontiers of knowledge, from the mythical dragons of medieval charts to the real abysses of the deep ocean. From the wandering dunes of the desert to the quiet data gaps where satellites can't quite see. Each chapter is another edge, a meeting point between what we know and what we sense but cannot yet name. This isn't a story of conquest or discovery. It's a gentle exploration of wonder itself, how the unknown shapes our imagination and our geography. So settle in, slow your breathing, and let your mind travel to the places the maps forgot. The night ahead is long, and there's still so much Earth left to find. If you look closely at a map, any map, you'll notice that it's really an act of confidence bordered by humility. Inside the neat lines and labels, humanity asserts, this we understand. But somewhere, just beyond the ink, is where certainty fades. The edge is not a cliff or a fence. It's a soft boundary where knowledge begins to blur. In ancient times, those edges were far closer than they are now. To early map makers, the world was smaller, cozier perhaps, and full of mystery. The Greeks drew circles of land surrounded by the endless Oceanus, imagining the known world as a kind of cosmic island. Claudius Ptolemy, working in the 2nd century, created maps that stitched together everything known to the Mediterranean world. Rivers, mountains, trade routes. But beyond them, there were gaps. He left space for imagination to breathe. His maps were mathematical marvels of their day, yet even they held vast stretches of terra incognita, the land unknown. Edges in this sense were invitations. They whispered possibilities. Maybe more land, maybe monsters, maybe gods. To trace a coastline or to follow a river upstream was not just exploration, it was a flirtation with the limits of understanding. As centuries rolled forward, coastlines became the first parts of the world to sharpen into focus. Medieval sailors, using compass bearings and the steady patience of experience, began to chart the outlines of continents long before they understood what lay inland. These charts, called portolans, were astonishingly precise along the edges of the sea. Every harbour, cape and shoal was drawn with care. Yet, as soon as you turned your eyes inland, the detail melted away into vague symbols and empty parchment. The map was saying, quite politely, "We're confident here and uncertain there." And that's really what edges are, where a map politely shrugs. The line between confidence and curiosity. The place where someone has to admit, we haven't been that far yet. Even today, our maps still carry the same quiet honesty. A map, no matter how detailed, is always a simplification, a compromise between the messy fullness of the world and the limits of paper or pixels. You can see it in the way the Earth must be flattened to fit on a page. Our planet is a sphere, but a map is not. Something must be stretched, squashed, or sliced to make it fit. Every projection, Mercator, Mollweide, Peters, carries its own distortions. Some enlarge the poles until Greenland looks like it could rival Africa. Others bend the oceans into subtle curves. There is no perfect projection because there is no perfect edge. The act of mapping is a choice, and every choice leaves something out. Even the notion of scale creates an edge of its own. A map of the world shows continents beautifully, but it forgets the details, the streets, the trees, the quiet corners where life happens. A city map does the opposite. It captures every alley and intersection, but loses the sense of where the city sits on the curve of the earth. To zoom in is to lose the big picture. To zoom out is to lose the intimacy. Somewhere in between lies the balance, but never the whole truth. The edges of maps are also psychological. They define where we feel safe and where uncertainty begins. The phrase "off the map" still carries a faint thrill, a mix of fear and fascination. It means stepping beyond the familiar. Long before GPS and satellite images, explorers like Ibn Battuta, Zheng He, and later the European navigators all felt this same magnetic pull, to see what lay past the next horizon. The blank spaces were not just physical voids, they were mirrors reflecting human curiosity. Cartographers through the ages have dealt with those blanks in creative ways. Some filled them with art, whales spouting fountains beside ships, dragons curling across imagined seas, and mountains that rose in fanciful ranges because no one had yet been there to argue otherwise. Others left the parchment empty, letting the absence speak louder than decoration. In a sense, both approaches were honest. Mystery has always demanded its own space. When you think about it, the edge of a map is also a kind of promise. It says, there is more beyond this line, and even when the line shifts outward, as our knowledge expands, the promise remains. For every mountain we've measured, there's another hidden under ice. For every canyon mapped, another waits in the ocean's darkness. The edge never truly disappears. It just moves. There's a quiet comfort in that. The world, vast as it is, still resists being fully known. The more we map, the more we realize how incomplete the picture will always be. And that incompleteness isn't a flaw, it's what keeps geography alive. Without mystery, maps would be little more than spreadsheets of space. Modern mapping has stretched the concept of edges in unexpected directions. Now, instead of ink on vellum, we use pixels, sonar, radar and satellite altimetry. Yet the challenge remains the same. To capture something round, rough and restless in neat straight lines. Beneath the world's oceans, mountains taller than the Alps rise unseen. trench systems twist deeper than the height of Everest. But much of this topography exists only as inference, guessed from the tiny gravitational tugs they exert on the sea surface above. It's a reminder that even our sleek digital maps are full of quiet approximations, an echo of those old compass roses. Edges also appear where human curiosity meets its limits of patience, funding, or technology. There are still regions so remote that mapping them would take more effort than reward. Jungle interiors, deep caves, or polar expanses. These are the modern terra incognita, places that shrug off satellites and sonar alike. Yet there's something poetic about that resistance. The world seems to insist on keeping a few secrets. It's as if the planet itself enjoys teasing us with mystery, shifting slightly each time we think we've finished the map. So when you look at a globe glowing softly in a darkened room, remember that it's less a record of certainty and more a portrait of human curiosity. Every edge, every faded border marks the place where someone once stopped and wondered, what lies beyond? And while the tools have changed from parchment and compass to radar and code, the feeling is timeless. The edge of the map is not an ending, but a conversation between what we know and what we long to understand. From the cartographer's quill tracing a trembling coastline to the modern sonar mapping the ocean floor, the same truth remains. Edges are where exploration begins. They're where knowledge meets possibility, where the world still leans softly into the unknown. The phrase, "Here be dragons," has slithered its way into our imagination so deeply that it feels like a universal symbol for the unknown. You can almost picture it. A curling banner on a yellowed parchment, warning sailors to stay clear of uncharted seas. It conjures adventure, danger, and mystery all at once. Yet, curiously enough, those exact words, hic sunt dracones, hardly ever appeared on actual maps. In fact, historians can only point to one surviving example, the Hunt Lennox globe, a small copper sphere from around the year 1504. On its eastern edge, near what we now call Asia, those famous Latin words appear, "Here are dragons," and that's about it. The rest of the myth is, ironically, one of cartography's best stories that never really existed. So how did the dragons get such a grip on our collective memory? It seems to come from a mixture of misunderstanding, metaphor, and the human love of good decoration. Early map makers didn't have the luxury of satellite imagery, but they did have plenty of imagination. When faced with a blank corner of the world, they had two options: leave it empty or fill it with something dramatic. And really, which sounds more fun, a bit of parchment or a sea serpent twisting round a ship? The seas on medieval and Renaissance maps were rarely quiet. They teemed with life, or at least with ideas of life. You'd find whales drawn the size of islands, leviathans swallowing entire vessels, and mysterious half-serpents rising from the surf. Some of these creatures came from travellers' tales. Others were lifted from bestiaries, those illustrated catalogues of real and imaginary animals that blurred the line between nature and myth. A few, like the giant squid or the orca, were based on misunderstood sightings of real creatures. Others were artistic license, a way to fill space and perhaps to remind anyone reading that the unknown could be both wondrous and terrifying. But there was also a practical side to these dragons and sea monsters. They weren't just there for decoration. They served as early warning systems. When a map showed a region full of writhing creatures or swirling winds, it was usually less about literal danger and more about navigational uncertainty. A cartographer might be saying, "We don't know what's here," and it might not be friendly. It was shorthand for risk, whether that meant storms, reefs, or pirates. Take the Olaus Magnus map of 1539, for example, a grand, detailed depiction of Scandinavia. It's famous for its population of remarkable sea beasts. There's a hairy fish that looks like a cross between a seal and a lion, a spiny creature that could pass for a dragon, and whales so large that sailors mistake them for islands. These weren't meant to deceive. They were warnings in picture form. Proceed with caution, because nature here behaves strangely. Some cartographers preferred winds over monsters. They used little human faces blowing across the oceans, each representing a prevailing direction. The north wind, the west wind, and so on. It made sense. To a sailor, wind was as alive as any creature, and just as unpredictable. A gust from the wrong direction could be as fearsome as any dragon's breath. There's also a subtle artistry in how these symbols appeared. The sea monsters weren't drawn randomly. They often marked regions where navigation was dangerous or poorly understood. Reefs near Iceland, the fog-shrouded North Atlantic, or the distant Indian Ocean. In that sense, they were an early form of data visualization. The more monsters you saw, the less the mapmaker knew. It was an elegant way of admitting uncertainty without leaving the page empty. It's worth noting that mapmakers themselves were rarely eyewitnesses. Many worked in studios far from the open sea. Their knowledge came second-hand, from explorers' journals, sailors' anecdotes, and occasionally, outright gossip. Imagine trying to make sense of reports that a fish bigger than a church was spotted somewhere west of Greenland. Without the ability to verify it, what could you do but turn it into art? A map was a story told in ink, and every good story needs a little drama. Yet, over time, those fantastical creatures began to retreat. As navigation improved and exploration filled in the blanks, the dragons lost their habitat. The Enlightenment brought a new kind of cartography, one focused on measurement, mathematics, and precision. By the late 1700s, the once vibrant oceans of maps became empty blue expanses, ruled not by monsters but by meridians and degrees of latitude. The imagination had given way to information. Still, it's easy to see why the idea of here be dragons survived, even if it wasn't really there. It captures something timeless about how humans face the unknown. When we reach the limits of knowledge, we tend to populate the dark with creatures of our own making. The phrase has become a metaphor not for fear, but for curiosity's frontier, the point where reason meets wonder. The persistence of the dragon myth in mapping also reminds us that old maps were never purely practical tools. They were philosophical statements. Each one reflected not only the world's geography, but its worldview. Medieval Europe's maps placed Jerusalem at the centre because it represented spiritual truth more than geographic accuracy. The margins, filled with creatures and strange lands, symbolised the outer limits of faith and familiarity. Dragons weren't just beasts, they were boundaries of belief. Even today, when we use the phrase "here be dragons," we're echoing that old cartographic honesty. We're acknowledging the limits of what we know, whether it's the deep sea, the human brain, or the far reaches of space. It's a poetic admission that there's always more to explore. In a way, those early map makers had the right idea. The monsters made the maps more honest, not less. They told you that certainty had its limits. They marked the places where the world still breathed mystery. Imagine turning a page in a Renaissance atlas, the parchment faintly yellowed, the ink a deep brown fading towards sepia. You'd see the familiar outlines of Europe, North Africa, perhaps the edge of Asia, crisp, confident lines. But beyond them, where the ink thins and the paper grows quiet, you'd find a creature coiled around a ship, or a wind face puffing its eternal breath. The room is still. The candlelight flickers. For a moment you can almost believe that somewhere out there the dragons are real. Not because they ever were, but because they gave shape to what we didn't yet understand. As sailors ventured farther and instruments grew steadier, these myths began to fade from the parchment. The world was growing larger, but the maps were becoming calmer. The dangers didn't vanish. They simply became better defined. The monsters, once drawn in curling ink, now hid beneath the waves as reefs and currents, still dangerous but finally measurable. The dragons retreated, but they left behind something precious, the reminder that imagination and exploration are inseparable. Every voyage begins with a question, and every question starts somewhere just beyond the edge of certainty. And while the old maps have long stopped warning sailors of dragons, the idea remains quietly true. There are still vast parts of our world where the lines blur, where the instruments flicker, and where the unknown waits patiently beneath the surface. No dragons required. Long before paper maps guided sailors across the seas, the ocean itself was the chart. Its swells, its stars, its shifting colours, all whispered directions to those who knew how to listen. For thousands of years before compasses spun and astrolabes glittered, navigators in the Pacific had already mastered the art of wayfinding, a form of mapping not with ink, but with memory. Imagine standing on the deck of a double-hulled canoe in the middle of the Pacific, somewhere between horizons. There's no land in sight, no compass, no sextant, just the rhythmic roll of the swells beneath your feet and the sky overhead scattered with stars like glowing breadcrumbs. To most of us, this would feel like drifting into uncertainty, but to a traditional Polynesian navigator, this was home. These oceanic explorers, voyaging between islands thousands of kilometers apart, relied on deep observational knowledge passed down through generations. Their tools were not compasses or coordinates, but rhythm, pattern, and instinct refined through study. The ocean to them was not chaos. It was a patterned surface, as readable as a book. They read the water first. Swells, the long undulations of the sea, move in predictable directions depending on where the wind and distant storms arise. An experienced navigator could feel multiple wave trains crossing each other and recognize the unique signature of his home island's reflection pattern. Even when land was hundreds of kilometers away, its presence changed the shape of the sea. The waves bounced off its reefs and returned faintly altered. By standing barefoot on the canoe and feeling that subtle interference in the rhythm of the swells, a navigator could sense where land must be. Then came the sky, the greatest map ever drawn. The star paths, known across Polynesia as the Kapehuhetu or star compass, divided the night sky into rising and setting points along the horizon. Each island group had its own version, but the principle was the same. The navigator memorized which stars rose and set along certain bearings. As the canoe moved, he tracked their arcs, knowing that when a particular star descended into the sea, he was travelling a specific course. Over a single night, dozens of these star paths could be read, forming a celestial grid invisible to the untrained eye. The technique demanded incredible mental discipline. Navigators often memorized hundreds of stars as well as their seasonal positions and the subtle shifts caused by latitude. A single cloudy night could erase the sky, but the ocean always offered backup clues. During the day, birds became messengers. The flight of terns, noddies, and frigate birds hinted at distance from land. Certain species never strayed far from their nesting grounds, while others ranged farther, returning in predictable patterns at dusk. Observing the direction they flew at sunset could reveal the location of islands beyond the horizon. Clouds too spoke their language. Land warms differently from water, creating distinct cloud formations. Over coral atolls, clouds often form high, puffy towers with flat bases from which one can catch the reflected colours of the lagoon. Even the hue of the sea told stories. A change from deep blue to a lighter turquoise might mean shallower reefs ahead. Every detail mattered. The taste of salt on the air, the scent of vegetation carried on a breeze, even the behaviour of ocean foam. The most astonishing part is that all this information was not written down. It was remembered, internalized, and recited in chants, songs and metaphors that transformed practical knowledge into poetry. A navigator might describe a star path as a bird's flight or a wave pattern as the beating of a drum. These metaphors help students of navigation remember not just directions, but relationships, a way of seeing the sea as an interconnected whole. One of the most beautiful artifacts from this tradition is the stick chart of the Marshall Islands, known as a rebelib. Made from thin sticks of coconut midribs lashed together with twine, these charts represented the relationships between islands and the patterns of swells that moved between them. The curved sticks showed the direction and shape of wave patterns, while small shells marked island positions. They weren't maps for carrying on voyages. They were teaching tools used on shore to train the memory. A student would study the rebelib until he could picture it in his mind, then leave it behind before setting sail. Once at sea, the real map unfolded beneath him. It's easy to romanticize this kind of navigation as mystical, but it was deeply scientific in its precision. Observations were tested, refined, and handed down only if they consistently worked. Errors could mean disaster. Yet remarkably, this system allowed voyagers to cross enormous distances, thousands of kilometers across the open ocean, centuries before European navigators ventured far from shore. Archaeological and linguistic evidence suggests that by about the year 1000, Polynesian voyagers had already settled nearly every inhabitable island in the Central Pacific, from Hawaii to New Zealand to Easter Island. These journeys weren't accidents. They required deliberate planning, timing, and knowledge of the seasonal winds and currents. Modern experiments, such as those by the Polynesian Voyaging Society with the canoe hokulea, have proven just how accurate these techniques remain. Using only traditional methods, no compass, no GPS, navigators have sailed from Hawaii to Tahiti and back, guided purely by stars and swells. It's a humbling reminder that navigation is as much about understanding relationships as it is about finding positions. Where Western cartography often relied on abstraction, grids, degrees, coordinates, Polynesian wayfinding relied on sensory immersion. The navigator became part of the environment, not separate from it. The canoe was an extension of the body, and the body a living instrument tuned to the sea. There's a quiet wisdom in that approach. It treats the ocean not as a barrier, but as a bridge. The Pacific, which seems so vast and isolating on modern maps, was once seen as a network of pathways, each island connected by invisible lines of memory and motion. To navigate was to participate in the rhythm of the world. The knowledge itself was sacred, often guarded and taught only to apprentices chosen for their patience and perception. Training could take many years. Students learned not by reading, but by doing, by sitting in the canoe night after night, feeling how the pitch of the vessel changed with each kind of swell, how the stars shifted slightly as the earth turned, how birds behaved differently before sunrise. Bit by bit they absorbed an internal geography. What makes this even more extraordinary is that such methods emerged independently across vast distances. In Micronesia, Melanesia and Polynesia, each culture refined its own system, some favouring star paths, others more focused on wave interactions or cloud formations. There was no single manual, no universal standard, just a shared language of attention. In a world that prizes written records, these oral systems remind us how powerful the human mind can be when tuned to its surroundings. The navigator's brain held an ocean-sized database, one built not on paper, but on repetition, rhythm, and respect for nature's clues. When Europeans finally entered the Pacific, they were stunned by the accuracy of island-to-island navigation. Many early explorers could not believe that anyone could cross such distances without instruments, but the evidence was undeniable. Islanders had done it for centuries. Their canoes, sleek and symmetrical, were the spacecraft of their time, capable of crossing worlds that to others seemed unbridgeable. To modernize, a map gives certainty, a line, a point, a label. But for these master navigators, certainty came from movement itself. Knowledge was not fixed. It lived in the waves and the wind. They did not need to draw lines to know where they were. They simply listened to the ocean's quiet language, and it told them. There's a kind of poetry in that, a gentle inversion of how we tend to think about maps. The Polynesian navigator didn't draw the world to understand it. He understood it so deeply that he didn't need to draw it at all. The art of wayfinding still survives today, preserved by cultural revival and taught in voyaging schools across the Pacific. Each new generation of navigators keeps alive an ancient truth, that maps are not always made of paper, and that direction can come from trust in the stars, in the sea, and in the steady rhythm of the earth itself. It was from this wordless mapping of waves and stars that the world's first precise charts would later emerge. The quiet art of feeling the sea would eventually give rise to the inked lines of coastal maps, the bridge between memory and measurement, between the living ocean and the drawn world. By the time the Middle Ages rolled around, the ocean was no longer an unmarked mystery, but a puzzle in need of precision. Trade was booming, ships were braving longer routes, and sailors were growing weary of maps that valued imagination over accuracy. Enter the Portolan chart, a new kind of map that transformed the way the sea was seen, measured, and mastered. It was, in its own quiet way, one of the great revolutions of geography. At first glance, a Portolan looks almost decorative, an intricate network of lines radiating from compass roses that bloom across the parchment like flowers of navigation. But those lines, called rum lines, were the secret to their astonishing accuracy. To the medieval sailor, each line represented a direction on the compass, northeast, southwest, and so on, neatly divided into 32 bearings. By aligning those lines with a known landmark, mariners could plot a steady course from one port to another. It was a visual translation of the magnetic compass, geometry made practical. What makes these charts extraordinary is just how right they were, centuries before the age of longitude and the invention of accurate timekeeping. Many early maps of the world were lopsided, distorted, or based on second-hand tales. Yet Portolans captured the shape of the Mediterranean and Black Seas with uncanny precision, so precise in fact that when modern geographers overlay them on satellite images, the coastlines nearly match. For maps created with nothing more than a compass, a rope, and a keen eye, that's no small feat. The earliest surviving example, the Carta Pisana, dates from around the year 1290. It appeared suddenly, without a clear predecessor, as if it had sprung from the sea itself. Scholars still debate where this leap came from. Genoa, Majorca, Venice. The truth is lost to history, but the impact was immediate. Every ship that traded spices, silks, and stories across the Mediterranean began carrying these charts. In an age before longitude, they offered a dependable way to travel by sight and by bearing, one coastal feature at a time. To create a Portolan, cartographers relied not on mathematics or celestial observations, but on the lived experience of sailors. Each harbour, cape, and bay was drawn where sailors knew it to be, based on their compass courses and estimated distances. A network of ports became a web of connections, gradually stitched together through practice and repetition. The result was a kind of collective memory, captured in ink. The Mediterranean was the perfect training ground for this experiment. Its enclosed seas, familiar winds, and dense clusters of ports made it possible to refine routes through centuries of observation. Mariners would hug the coast, following its curves and noting landmarks as they went. The moment a new feature was verified, a cliff, a lighthouse, a distinctive mountain, it found its way onto the next chart, Slowly, the jagged puzzle of Europe's coastline took shape, each bay and peninsula drawn tighter into focus. If you trace your finger across a portolan, you can feel the rhythm of movement it represents. From Barcelona to Tunis, from Crete to Alexandria, every line tells of a voyage. Ships of the time rarely ventured far from shore. Instead, they followed a dance of bearings, measuring direction by the needle of the magnetic compass, a tool imported from the East that transformed navigation. Its principle was simple. The magnetized needle pointed north, but its implications were profound. It gave direction to the sea itself. When combined with the rhomb lines on the chart, the compass turned the ocean into a navigable grid. A sailor could say, "From this port steer northeast for 2 days," and have a reasonable chance of arriving somewhere intentional rather than accidental. Before that, sailing was often more art than science, relying heavily on landmarks, local pilots, and fair weather. The portolan made the sea predictable, or at least slightly less capricious. Each chart began with a circle of intersecting rhumb lines radiating from a central point, like the spokes of a wheel. Soon, more circles were added, each overlapping the last, creating a dense web of lines stretching across the parchment. The pattern was mesmerizing, a geometry of movement that looked chaotic but wasn't. Every line had purpose, and every intersection could guide a ship from one compass heading to another. The artistry of these charts is part of their charm. The parchment, usually made of treated vellum, was smooth and durable, perfect for rolling and unrolling in the damp air of a ship's cabin. The coasts were inked in earthy browns or blacks, with shallow waters tinted green and deeper seas left pale. Place names marched inland at right angles to the shore, so they could be read easily while the map lay flat on a table. Compass roses, often lavishly decorated, added splashes of red and gold. But beneath the beauty was functionality, the same practical genius that defines great design even today. Despite their coastal precision, portolans remained curiously indifferent to the land beyond. Once the coastline ended, the mapmaker's confidence dissolved. Mountains were sketched vaguely, rivers meandered without clear source or destination, and entire kingdoms might be represented by a single castle. The sea was the true subject, and everything else was background decoration. The charts mirrored the mindset of their users, sailors who trusted the ocean more than the unknown terrain inland. It's intriguing that while medieval Europe often portrayed the sea as dangerous or chaotic, portolans reflected a quieter truth, the sea as something knowable. Their tone was pragmatic, not poetic. No dragons guarded these waters, no allegorical beasts lurked in the margins. Where earlier maps had warned, "Here be monsters," portolan simply said, in effect, "Here is Sardinia, 40 nautical miles east." The age of myth was slowly giving way to the age of measurement. Still, even the most meticulous portolan had its quirks. Because they relied on magnetic bearings rather than true geographic north, they carried a small but consistent distortion. Over long distances, lines that looked straight on the map curved subtly on the globe. Yet for the sailors of the 14th century, that distortion was invisible and irrelevant. What mattered was that it worked. Accuracy wasn't measured in degrees, but in safe arrivals. These charts spread quickly beyond the Mediterranean. As trade routes extended through the Atlantic and into the Indian Ocean, new coastlines were added, stitched onto the growing fabric of the world's knowledge. Venetian, Genoese and Majorcan chart makers competed for prestige, adding layers of information, currents, landmarks, even political symbols. By the time explorers like Columbus and Vasco da Gama set out, they were following in the wake of centuries of careful observation. The portolan was their compass in 2 dimensions. Even now, when you see one of these old charts in a museum case, it feels alive. The parchment ripples slightly, as if remembering the sea breeze that once ruffled it. The inked coastline still seemed to shimmer with salt. It's hard not to be impressed by their audacity, a blend of art, science, and trust in human senses. They remind us that mapping is not just about drawing what's seen, but about believing that order can be found in the unknown. The invention of the portolan was, in essence, the moment the ocean gained structure. Before it, sailors moved through guesswork and memory. After it, they had a system, a language of lines that allowed the sea to be measured, shared, and eventually mastered. And yet, for all the confidence those lines brought, the maps still fell silent as soon as they reached land. Beyond the drawn coast, the interior remained pale and empty. A whisper of hills, a hint of rivers, but nothing more. The sea had been claimed by geometry, but the heart of the continents was still waiting to be heard. For centuries the world's maps were haunted, not by sea monsters this time, but by islands, beautiful, promising, and entirely imaginary. They dotted charts like phantom stars, each one waiting to be discovered, each one destined to quietly disappear. Some lasted for decades, others for hundreds of years, defying correction through sheer repetition. And while the age of satellites has finally thinned their ranks, a few still linger in the half-light between myth and measurement. One of the most famous ghosts is High Brazil, a mysterious island said to lie somewhere west of Ireland. It first appeared on maps as early as the 1300s, sometimes round, sometimes crescent-shaped, but always just out of reach. Sailors claimed it was cloaked in mist, visible only once every 7 years, which seems a rather convenient schedule for something that doesn't exist. Yet High Brazil held on stubbornly. Well into the 1600s, explorers set sail in search of it. They returned empty-handed but not disheartened. After all, perhaps the island was simply hiding. Some said it was the home of advanced people. Others swore it was enchanted, a kind of Celtic Atlantis. It became for a while one of geography's most elegant illusions. These phantom islands weren't always born of legend. Many were the result of simple mistakes, errors in latitude, longitude, or the unpredictable behaviour of the sea itself. A captain might spot what looked like land in the distance, jot down its position and sail on. Later, another navigator would read that note, copy it onto his own map, and suddenly a patch of ocean had a name. The problem wasn't the mistake, it was the repetition. Once something appeared on one respected chart, it was copied onto others, and others after that. The map-making world was surprisingly good at recycling its own errors. Mirages also played their part. In polar regions, atmospheric refraction can lift distant icebergs or coastlines above the horizon, creating the illusion of floating islands. In warmer waters, heat and humidity can bend light so dramatically that clouds, fog banks, or even ships appear to take on the shape of land. Early sailors didn't have the luxury of double-checking such visions. When you've been staring at endless water for weeks, a faint outline on the horizon is irresistible proof of hope, and so, one by one, these hopeful mirages became inked realities. Take Freeland, for instance, a sprawling, oddly shaped island that appeared just south of Iceland on maps for nearly 300 years. It showed up in the Zeno map of 1558, supposedly based on voyages by 2 Venetian brothers. For generations, cartographers faithfully included it, sometimes even giving it towns, harbours, and mountains. But no ship ever landed there, because it wasn't there. Some historians think the Zeno brothers misidentified part of Greenland, or perhaps mistook a mirage for solid ground. Either way, Friesland enjoyed a long and comfortable career as a non-existent country before quietly vanishing from maps in the 18th century. Then there's the more recent case of Sandy Island, a ghost from the modern age. It appeared on digital charts between Australia and New Caledonia, first recorded by the whaling ship Velocity in 1876. The ship's captain marked its position carefully, and that was enough to secure its place on global maps. It was even included in authoritative databases and later found its way into Google Earth. For over a century, it lived quietly among the Pacific Islands, unvisited and unquestioned, until a scientific expedition in 2012 decided to check. When their vessel arrived, they found only open water. The island simply wasn't there. One geologist described the moment as eerily beautiful, a perfect patch of sea where something was supposed to be. The team jokingly dubbed it the Invisible Island. The data was corrected, and Sandy Island vanished overnight from digital cartography. That's the curious thing about errors. They can be as persistent as truths. Once recorded, they gain authority, and authority spreads faster than skepticism. In the age before easy verification, copying was safer than questioning. A map full of small inaccuracies still looked more complete than one full of gaps. And so the ghosts multiplied. Islands that were too far north, too far south, duplicated under new names, or invented wholesale to fill uncomfortable empty spaces. Some of these phantom lands were deliberately placed. In the 19th century, a few publishers added fake features to their maps, small bends in rivers, non-existent islands, or made-up towns, as copyright traps. If a competitor's map copied those same details, the plagiarism would be obvious. The practice was a bit of cartographic mischief, falsehoods used to guard the truth. Even today, a few modern digital maps are rumoured to contain similar tricks. An invisible lane here, a phantom cul-de-sac there. Small reminders that maps are as human as their makers. But there's also a more poetic reason these ghost islands persisted. We wanted them to exist. In the long centuries of exploration, empty ocean was disappointing. A blank stretch of blue felt like wasted potential. Adding an island made the world seem fuller, friendlier, more symmetrical. Every phantom island was a kind of wish, a hopeful gesture that maybe the unknown still held surprises, and in some cases these illusions had real consequences. Explorers wasted months searching for islands that weren't there. Ships diverted off course, burning supplies and morale, chasing coordinates that led only to endless waves. Even as late as the 20th century, naval charts still included doubtful islands marked with cautious notes like reported 1884 or existence questionable. It's a wonderfully polite way of saying, we've no idea if this thing is real, but we'll leave it just in case. Science eventually began to clear the fog. The development of precise timekeeping in the 18th century allowed longitude to be measured accurately for the first time. Later, aerial photography, radar, and finally satellites turned the ocean into a grid of data. Each innovation chipped away at the ghosts. Modern satellites can detect islands just a few meters wide by measuring how gravity slightly bulges the sea surface above them. The oceans, once full of imagined lands, are now mapped to a precision that would astonish any medieval cartographer. Yet the disappearance of phantom islands doesn't mean the end of mystery. There's a strange nostalgia attached to them, as if their vanishing took a little bit of romance from the sea. When the scientists confirmed that Sandy Island didn't exist, there was an odd sense of loss, a collective sigh that one more pocket of wonder had been tidied away. Some islands, it seems, are extremely shy. They prefer to live in stories rather than on charts, and in their absence they remind us of something deeper about maps. They are, at heart, human documents. Each one reflects not just the world as it is, but as we believe it to be. A map without mistakes would be a map without imagination, and perhaps without warmth. The ghosts, the guesses, the hopeful errors, they all tell us how much we've wanted to understand the world, even when our evidence was thin as mist. Today, the oceans are still capable of playing tricks. Ships occasionally report strange readings from sonar or radar, false returns that suggest hidden shoals or rises that later prove to be clouds of fish, or layers of warm and cold water bending sound. Even in the data-driven 21st century, the sea occasionally winks, reminding us that it hasn't told us everything. The phantom islands may have disappeared from our maps, but their spirit lingers in the way we still search for what isn't there. Every lost coordinate, every unexplained echo, every faint line that refuses to match the model. All of them carry a whisper of High Brazil and Sandy Island. They are echoes of a time when to explore was to imagine, and when even a mirage could become a place. And perhaps that's the charm of these vanishing lands. They show that knowledge doesn't only expand by discovery, it also deepens through correction. Every time a phantom fades, our picture of the world becomes a little clearer, and yet somehow the mystery only grows, because for every island erased, there's another still waiting, hidden not above the waves, but somewhere far below, where the map once again begins to blur. Beneath the ocean's surface lies a landscape grander than anything on land, mountain ranges that dwarf the Himalayas, trenches deeper than any canyon, and plains vast enough to swallow continents. Yet for all its immensity, it remains, for the most part, unseen. More than 70% of Earth's surface is covered by ocean, and yet we've mapped less than a quarter of its floor in high detail. In an age of satellites, lasers, and interplanetary probes, it's strange to think that we know the terrain of Mars better than the world beneath our own waves. The reason isn't mystery so much as difficulty. Mapping the seafloor is an exercise in patience, physics, and persistence. Water, as it turns out, is a terrible medium for seeing through. Light disappears within a few hundred meters, radio waves barely penetrate, and even radar, the backbone of modern mapping, skims uselessly across the surface. To map the ocean floor, we have to listen instead of look. That's where sonar comes in. The principle is elegantly simple. Send a pulse of sound down through the water, wait for it to bounce off the bottom, and time how long it takes to return. Multiply that by the speed of sound in seawater, roughly 1,500 meters per second, and you have the depth. Do this once, and you know how deep it is at that spot. Do it millions of times in overlapping swaths, and you can build an image of the landscape below. Modern ships use what's called multi-beam sonar. Instead of firing one sound pulse straight down, it emits a fan-shaped array, covering a wide strip of seafloor beneath the vessel as it moves forward. Each ping, sometimes hundreds per second, creates a ribbon of data. Over hours and days, those ribbons weave together into a tapestry of topography. The hum of the engines, the gentle sway of the ship, and the rhythmic ping, ping, ping of the sonar create an oddly hypnotic soundscape, the music of underwater mapping. But even this powerful method has limitations. A single research vessel can only map a narrow strip of ocean at a time, and the ocean is unimaginably vast. At current rates, a full high-resolution map of the seafloor could take centuries to complete. Most of the data we have so far comes from narrow corridors, shipping routes, areas near coasts, or regions of scientific interest. The rest is, quite literally, still guesswork. To fill in those gaps, scientists use another approach: satellite altimetry. While satellites can't see through water, they can measure the height of the sea surface with astonishing precision, down to a few centimeters. And that, surprisingly, reveals what lies beneath. The seafloor's mountains and trenches subtly tug on Earth's gravity, causing tiny bulges or dips in the ocean above them. A seamount, a kind of underwater volcano, creates a slight gravitational pull, drawing a mound of water upward. A deep trench does the opposite, creating a dip. By measuring these variations, satellites can infer the broad shape of the seabed. This technique has given us a global map of ocean basins at a resolution of about 10 kilometers. It's impressive, but it's also a bit like trying to draw a mountain range with a thick paintbrush. You'll get the general form, the peaks, the valleys, but not the fine detail. The smaller ridges, canyons, and seamounts simply blur into suggestion. To truly see them, you need sonar, and sonar takes time. Mapping ships must move slowly, usually around 10 knots, to ensure accurate readings. They operate around the clock, their crews working in shifts under red lights that keep the eyes adjusted darkness. Each voyage can last months. The data collected must then be cleaned, processed and corrected for variables like water temperature, salinity, and even the curvature of the Earth. It's a monumental task, one reason why only a small fraction of the seafloor has been mapped in detail. There's also the matter of expense. Oceanographic research ships are costly to operate, and their missions are limited. They must share time between geological mapping, biological studies, climate monitoring, and other priorities. The ocean is in effect too large for our current Curiosity budget. Yet despite the gaps, what we have learned from the portions we have mapped is breathtaking. The mid-ocean ridges, for example, the great underwater mountain chains that circle the globe, were first revealed through early sonar surveys in the 20th century. These ridges mark the boundaries where tectonic plates pull apart, birthing new crust and reshaping continents. The discovery helped confirm the theory of plate tectonics, one of the great scientific revelations of modern geology. Elsewhere, sonar has uncovered enormous undersea volcanoes, submarine canyons carved by ancient rivers, and flat-topped mountains called guyos that tell stories of drowned islands and vanished reefs. The Mariana Trench, the deepest known point on Earth, plunges nearly 11,000 meters, so deep that if Mount Everest were dropped into it, its summit would still be 2 kilometers underwater. And yet, compared to the rest of the ocean, the trench is one of the better mapped places. In recent years, autonomous underwater vehicles, robotic explorers equipped with sonar, have joined the effort. They can dive deep, stay out for long stretches, and cover areas too remote for ships. Still, their range is limited, and they can't match the endurance of large mapping vessels. Some researchers dream of fleets of robotic mappers, quietly sweeping the oceans in coordinated patterns, their data stitching together into a seamless picture. For now, though, the dream remains just beyond the horizon. It's easy to forget that all this effort is happening in almost total darkness. Below about 1,000 meters, sunlight disappears entirely. The temperature drops, the pressure builds, and life adapts into strange and beautiful forms, creatures shaped by a world of perpetual night. Each new patch of seafloor we map reveals more than geology. It reveals the context for these hidden ecosystems, the foundations of the planet's largest biosphere. The ocean floor is as alive as it is unknown. The importance of mapping it goes far beyond curiosity. The seafloor controls how heat moves through the ocean, influences currents and climate, and even determines where tsunamis and earthquakes might strike. Submarine landslides, often invisible to us, can generate waves that race across entire oceans. Cables carrying global internet traffic snake along the seabed, crossing ridges and valleys. Oil, gas and mineral deposits hide in its sediments. The ocean floor, unseen as it is, underpins much of modern civilization. Yet there's a quiet irony in how difficult it remains to see. We have mapped the entire surface of Venus through clouds of sulfuric acid. We have precise topographies of Mars, the Moon, and even some distant asteroids. But the Earth's own depths, just a few kilometers below our feet, remain an enigma. The ocean guards its secrets well. Still, that secrecy is slowly eroding. Projects like Seabed 2030 and international collaboration aim to map the entire ocean floor in high resolution by the year 2030. Thousands of scientists, mariners, and volunteers contribute sonar data, much of it collected incidentally by ships on other missions. Every fragment helps. Each new survey, no matter how small, fills another gap in the great underwater mosaic. It's a quiet revolution, unfolding beneath the waves. And for those who've spent nights on a mapping vessel, there's something deeply meditative about it. The world above sleeps while the instruments below sing to the deep. The sonar's rhythmic ping is a conversation between ship and seafloor, a dialogue stretched over kilometers of black water. Bit by bit the echoes return, painting the unseen world in sound. In the end, mapping the seafloor isn't just about discovery, it's about humility. It reminds us that even on our own planet, vast domains remain out of sight. The Earth we know is only the upper crust of something grander and more mysterious. The ocean floor with its mountains and plains is a world unto itself, as deserving of wonder as any alien planet. And somewhere far below, under pressure so great it would crush steel, the continents continue to drift, the ridges continue to grow, and the planet keeps reshaping itself in the darkness. The sea has given up much, but not yet everything. Beyond those rippling echoes and rhythmic pings lie other hidden landscapes, ones that wait patiently, buried beneath the ice, for their turn to be revealed. Beneath Antarctica's endless whiteness lies a hidden world, sealed away for millions of years. If you could somehow slip below that frozen roof, you wouldn't find a solid block of ice, but a living landscape. Mountains, valleys, rivers, and even vast lakes, all buried under ice sheets that can be more than 4 kilometers thick. It's a strange, secret version of Earth, humming quietly in the dark, where glaciers flow like slow rivers, and entire mountain ranges lie entombed, unseen by human eyes. The first hint that something extraordinary existed below came not from explorers on the surface, but from sound waves. In the mid-20th century, scientists began bouncing radar pulses off the Antarctic ice. Most of the signals returned as expected, reflecting the boundary between air and ice, but some went deeper, echoing off something far below. Beneath thousands of meters of frozen weight, the radar revealed a hidden interface, a place where the ice met bedrock, and where, to everyone's surprise, the ice wasn't all frozen solid. In certain places it was floating above liquid water. Those discoveries led to one of the great geographical revelations of modern times, the existence of subglacial lakes. The largest of them, Lake Vostok, lies under nearly 4 kilometers of ice in East Antarctica and stretches roughly 250 kilometers long, about the size of Lake Ontario. It has likely been sealed off from the surface for at least 15 million years. The pressure of the overlying ice, combined with geothermal heat rising from the Earth's crust, keeps the water liquid despite the intense cold. It is in every sense an alien environment, cut off from sunlight, oxygen, and most of what we would consider normal life. For decades, scientists could only imagine what might live there. When samples were finally extracted from the lake's icy cap, they found traces of microbial life, organisms adapted to survive in complete darkness, under immense pressure, and at temperatures just below freezing. Whether they truly came from the lake itself or from ancient sediments above it is still debated, but their presence suggests that even the most inhospitable places on Earth may harbour life, and Lake Vostok is only the beginning. More than 400 subglacial lakes have now been identified beneath Antarctica, connected by a network of hidden rivers and channels. Some are large, others no bigger than ponds. They don't sit still either. Water beneath the ice moves, draining and refilling as glaciers slide above. When scientists first observed these fluctuations by satellite, they realized that parts of the ice sheet behave like a giant slow-motion plumbing system. It was a revelation. Antarctica isn't frozen in place, it breathes. The continent's secret geography extends far beyond lakes. Beneath the thick ice of East Antarctica lies one of the most mysterious mountain ranges on Earth, the Gamburtsev Mountains. Discovered in the 1950s by Soviet researchers, this vast range rivals the Alps in height and scale, yet it's entirely invisible from the surface. Radar and seismic studies reveal sharp peaks, deep valleys, and broad plateaus, all entombed beneath 3 kilometers of ice. How such dramatic topography survived under that crushing weight is still debated. Some think the mountains formed more than 1 billion years ago and were later preserved by the ice that covered them, like a fly frozen in amber. Others believe they were rejuvenated by more recent tectonic activity before being sealed away. The image is haunting, a mountain range taller than anything in Western Europe, locked away beneath a frozen desert the size of a continent. If the ice were to melt, a scenario not likely anytime soon, the Gamburtsevs would rise into daylight for the first time in human history, their peaks glistening after millions of years in darkness. For now, they remain ghosts, known only through the echoes of radar pulses and the faint tug of gravity measured by satellites. The technology used to explore these hidden worlds is remarkable in its subtlety. Airborne radar instruments, mounted on planes or satellites, send electromagnetic waves that can penetrate ice and reflect from the bedrock below. By timing the return of the signal, scientists build detailed cross-sections of the ice sheet, revealing its thickness, layers, and the shape of the terrain beneath. Sometimes the radar even detects the faint shimmer of water, smooth, reflective, unmistakable. When combined with ice-penetrating lasers and seismic sensors, the result is a kind of X-ray vision for the planet. These surveys have uncovered a dynamic system. Deep within the ice sheet, rivers flow beneath the glaciers, lubricating their movement. The water acts like oil on a massive machine, reducing friction and allowing the ice to slide faster toward the sea. These are the so-called fast ice streams, broad, slow-moving rivers of solid ice that can travel several meters a day. They carve channels into the bedrock, transport enormous amounts of sediment, and play a major role in how the ice sheet drains. Some are stable, others surge unpredictably, releasing vast floods of water into the ocean. Scientists have even observed sudden ice quakes as the frozen mass shifts under its own immense weight. The noise of Antarctica is not silence but tension. The groan of ice against rock, the muffled crack of crevasses forming, the faint trickle of meltwater running unseen below. Imagine standing on the surface surrounded by endless white, while far beneath your feet, rivers move in darkness, shaping valleys no human has ever seen. It's a thought that shrinks perspective. These hidden landscapes also hold crucial clues to Earth's past and future. The sediments trapped under the ice record ancient climates, capturing chemical fingerprints of times when Antarctica was green and forested. By drilling cores from the ice and bedrock, scientists can trace the planet's climate back millions of years, learning how ice sheets grow and retreat. Understanding that history helps predict how the modern world's glaciers might respond to warming oceans and shifting temperatures. Beneath the stillness of the Antarctic plateau, the story of Earth's climate is written layer by layer, flake by flake. And despite the cold, the story is far from static. Satellite data now show that Antarctica's ice is thinning at its edges, particularly around West Antarctica, where warmer seawater is eroding the glaciers from below. Hidden cavities are opening up beneath the ice shelves, and subglacial lakes are changing their volumes more rapidly than ever observed. The continent's underworld, once thought timeless, is revealing itself to be surprisingly dynamic, a frozen engine responding to the planet's slow fever. There's a quiet irony in how we discover all this. To see beneath the ice, we rely on echoes. tiny pulses of energy that bounce through kilometers of frozen history. Each return signal, each faint reflection, tells of a mountain ridge, a buried valley, or a hidden lake. The data looks like static on a screen, but within it are landscapes of astonishing complexity. We are, in essence, learning to listen to the ice itself, and there's still much more to hear. The Antarctic and Greenland ice sheets together cover about 1/10 of Earth's surface, and vast portions remain poorly mapped. As radar instruments improve, new features appear: hidden basins, under-ice volcanoes, networks of channels that may one day feed rising seas. The deeper we look, the more intricate the frozen world becomes. To study these places is to glimpse a paradox. The ice, which seems eternal, is in constant motion. It creaks, flows, melts, and refreezes, shaping the land it conceals. The mountains and valleys below, untouched by light for millions of years, continue to evolve under that heavy shifting blanket. The continent breathes, slowly but powerfully. Antarctica's buried topography is a reminder that the map of Earth is still incomplete. Even in an age of satellites, there remain worlds so hidden that only their echoes reach us. Beneath the ice's filtered blue light lie cathedrals of stone and valleys carved by time, waiting in the cold and the dark, patient as the planet itself. And just below those frozen roofs, the ground holds its own quiet geography, one that will someday perhaps awaken when the ice finally lets go. Beneath our feet, the world is hollow, not empty exactly, but full of passageways, chambers, and rivers that twist through the rock like the planet's hidden veins. This subterranean realm, the underworld of limestone and water, is one of Earth's last great frontiers. New caves are being discovered every year, and existing ones keep growing as explorers crawl, climb, and sometimes even dive into the darkness. Yet for all our mapping skills, the underground remains stubbornly elusive. It's not that we lack technology, it's that the Earth, quite literally, doesn't make it easy to go vertical. Caves are born from patience and chemistry. Most begin in limestone, a rock made largely of calcium carbonate, the compressed remains of ancient marine creatures. When slightly acidic rainwater seeps into cracks, it begins to dissolve the stone, molecule by molecule. Over thousands or millions of years, those cracks widen into fissures, fissures open into tunnels, and tunnels bloom into caverns. It's a process called speleogenesis, and it's one of nature's slowest acts of sculpture. Limestone is particularly susceptible to this gentle corrosion. Carbon dioxide from the atmosphere and soil mixes with water to form carbonic acid, weak but persistent. As the acid percolates downward, it etches the stone into fantastical shapes, shafts, domes, and passages that seem to obey no logic except gravity. Where the water table fluctuates, these features stack into multi-level labyrinths, creating systems that can stretch for hundreds of kilometers. One of the most extraordinary examples lies in Kentucky, the Mammoth Cave System, the longest known cave network on Earth. So far, over 650 kilometers of passages have been mapped, yet explorers estimate there's only a fraction of the total. Each new survey adds more corridors, more connections, as if the ground is slowly unfolding. It's a reminder that caves don't sit still, they evolve. Water continues to carve new routes even as explorers try to trace the old ones. Elsewhere, in places like Vietnam's Phong Nha Ke Bang and China's Guangxi province, the landscape rises instead of falls. These regions are known for karst topography, towering limestone spires, sinkholes, and deep dolines formed by the same dissolving forces that create caves. The karst towers, some rising hundreds of meters, are the remnants of a landscape that has been eaten away from below, leaving pillars of resistant rock standing like forgotten monuments. Beneath them lie networks of rivers that vanish underground, re-emerging kilometers away in turquoise springs. Mapping these systems is a monumental challenge. Unlike the open sea or the polar ice, caves resist the very concept of straightforward surveying. GPS signals can't penetrate rock, compasses can misbehave near magnetic minerals, and the paths themselves often demand contortion rather than navigation. A single misstep can mean a flooded passage, a dead end, or a crevasse too narrow for even the bravest explorer. Maps dislike places that go vertical, as one caver once joked. It's both true and mercifully understated. The process of charting a cave still relies heavily on human effort. Cavers use lasers and measuring tapes, sketching as they go, often by hand, in mud-smeared notebooks. Digital scanners are improving things, creating 3D models of complex spaces, but they're slow and unwieldy. Underground, everything conspires against precision. Dripping water, unstable footing, and air so humid that electronics fog and batteries fail. A single kilometre of progress might take days of crawling, climbing and squeezing. And because caves are often fragile ecosystems, home to delicate minerals, blind fish and ancient formations, every step must be careful. Mapping the underworld is as much an act of respect as exploration. Even when mapped, caves are difficult to define. What counts as a single system? Two neighbouring caverns may be connected by a passage just a few centimetres wide, invisible to us but open to water. Over time, those hidden links widen, and what were once separate caves merge into one sprawling complex. The world's longest caves are less static monuments and more living networks, constantly growing, splitting, and rejoining as the underground water shifts its course. Some of the most breathtaking systems are still barely explored. In 2009, a team of British cavers entered Hang Son Doong in Vietnam, a cave so vast it contains its own forest, clouds, and weather system. It stretches over 9 kilometres long, with passages more than 200 metres high. Inside, collapsed ceilings allow sunlight to stream through, nurturing entire ecosystems of mosses and ferns. The explorers described walking through it as entering another planet, one where time and scale bend in ways that make even the grandest cathedral seem small. And astonishingly, there are likely other chambers nearby, still sealed behind rock and rubble waiting to be found. Not all cave exploration happens in dry corridors. Many of the world's largest networks are partly underwater, formed where fresh and salt water mingle. So-called blue holes, or flooded sinkholes found in places like the Bahamas, Mexico's Yucatan Peninsula, and the Philippines. These submerged caves are treacherous, demanding expert diving skills and nerves of steel. In the narrow, twisting tunnels, visibility can vanish in an instant if a diver stirs up sediment. Yet these places are priceless archives of Earth's past, preserving fossils, artifacts, and even ancient human remains in their oxygen-poor depths. Each new descent adds another layer to our understanding of how sea levels and climates have changed through time. Karst regions, meanwhile, extend across roughly a quarter of the world's land surface. From the Balkans to Borneo, they create some of the most dramatic and least understood landscapes on Earth. Their hydrology is famously chaotic. Rivers vanish into sinkholes, run unseen through underground galleries, and reappear miles away. This makes them notoriously difficult to manage for drinking water, agriculture, and infrastructure. One moment a stream is steady and dependable. The next it disappears into the ground without a trace. It's geography with a sense of humour. Caves also hold delicate formations called speleothems, stalactites, stalagmites, flow stones, each one a geological timekeeper. Layer by layer, as water drips through the rock, minerals crystallize, recording shifts in temperature and rainfall over tens of thousands of years. Scientists study their isotopes to reconstruct past climates, turning cave drips into time machines. It's humbling to think that what looks like decoration is really data, frozen mid-drop. For all their wonder, caves are among the least accessible parts of our planet. Many are so remote or dangerous that no one may ever reach them. Some are blocked by collapsed ceilings, others by water too deep or tight passages too narrow. Technology helps, but even drones and robots struggle in such environments. The best maps we have of some of the largest cave systems are still sketches. Beautiful, approximate, and inevitably incomplete. The underground, it seems, enjoys its privacy, and yet our curiosity keeps pulling us down there. Humans have always been drawn to the underworld, both physically and symbolically. Ancient peoples saw caves as portals to other realms, places of birth, death, and transformation. Today's explorers may be less spiritual, but the sense of awe remains the same. To step into a cave is to enter a realm that defies sunlight, where sound travels strangely and time seems to slow. The walls glisten with minerals. Water drips like a metronome. The air smells faintly of stone and history. The hidden rivers beneath karst landscapes continue to sculpt new corridors, connecting and erasing boundaries as they go. Whole mountains can collapse inward over millennia, leaving sinkholes so vast they form forests of their own. Somewhere above ground, a gentle stream may vanish into a fissure, beginning a journey through the dark that ends miles away in a spring of crystal clear water. The Earth is constantly recycling its own geography, turning solidity into motion, and then back again. For now, our maps can only hint at this underground complexity. The lines we draw on the surface say little about the voids below, where space itself twists in unpredictable directions. But perhaps that's fitting. The world beneath us was never meant to be tidy. It's the planet's hidden architecture, a realm carved by water, polished by time, and still growing in secret. So the next time you walk across limestone country and feel the ground echo faintly beneath your steps, remember, you're walking over rivers that flow in darkness, through caverns older than civilization where the maps fall silent and gravity has the final word. And when those underground paths eventually resurface, emerging as springs or cliffs or unexpected hollows, they remind us that every journey through the earth, like every map, has its reversals. From these underfoot voids, the world turns upward once more, toward the forests that cling to the light. High above the forest floor there exists another world, a vast living ceiling of leaves, branches, and drifting mist. To walk among the treetops of a tropical forest is to step into an atmosphere that is neither sky nor earth, but something in between, a realm of filtered light, humming life, and perpetual moisture. It is one of Earth's most intricate ecosystems, and one of the hardest to map. The canopy is a continent of its own, stretching unbroken for kilometers at a time. Every branch, every patch of moss forms part of an elaborate architecture, where sunlight, rain, and air meet in delicate balance. But from above, even our most powerful satellites struggle to see what's really there. Clouds gather almost daily over equatorial forests, obscuring the view, and fog condenses in the thin air of mountain jungles. From orbit, these forests appear as a green blur, a uniform expanse. The fine details, the subtle layers that make them so alive are hidden in the haze. That's where the science of mapping meets the art of patience. Traditional aerial photography can capture the canopy's surface but not its depth. Radar can pierce clouds, but its wavelengths bounce off water and metal more than leaves. So, scientists turn to light itself, specifically to LIDAR, or light detection and ranging. It's a technology that measures distance by firing pulses of laser light and timing how long they take to bounce back. Each pulse can reflect off multiple surfaces, first the top leaves, then the branches, then the forest floor. When combined, those returns create a three-dimensional portrait of the forest. It's a remarkable form of vision. Where the human eye sees only green chaos, LIDAR paints a world of structure. It reveals the vertical layers of vegetation, the gaps in the canopy where new growth is pushing upward, and even the subtle undulations of the land beneath. Scientists call these variations micro-relief, the hidden topography under the trees that shapes how water and nutrients move. Rivers twist unseen beneath the green, and ancient terraces long swallowed by vegetation emerge as faint ridges in the data. One of the most striking discoveries from LIDAR mapping came not from ecology, but archaeology. When researchers scanned sections of jungle in Guatemala and Cambodia, the laser pulses revealed entire cities hidden under the trees, temples, roads, and canals, all overgrown yet perfectly preserved in the data. The forests had hidden human history for centuries, their roots entwined with forgotten civilizations. But LIDAR also uncovered something deeper, the scale of life itself. When used for ecology, it shows just how densely populated these forests are, not with people, but with species. Tropical canopies are biodiversity hot pixels, tiny areas where life reaches its highest concentration. A single hectare can contain more tree species than all of Europe. Every layer supports a unique community. Insects in the leaf litter, amphibians in the understory, birds and mammals among the branches, orchids and mosses clinging to the outermost twigs. In cloud forests, where altitude brings constant moisture, this vertical stratification becomes even more pronounced. Plants grow on other plants. Entire ecosystems live suspended in air. The canopy catches mist like a net, distilling it into droplets that drip down, feeding the trees below. To explore these worlds, scientists build rope bridges, cranes, and even canopy walkways that stretch between trees like suspended paths through a dream. Up there, the air feels different, cooler, more alive, saturated with scent and sound. You can hear the faint patter of condensed water dripping from leaves, the flutter of wings, the distant croak of unseen frogs. Every step is careful, not just for safety, but out of respect for how crowded with life each square meter can be. Mapping such richness is as much philosophy as science. You can't capture the soul of a forest in a grid of coordinates, but you can trace its patterns. The goal isn't just to measure trees, it's to understand how energy flows through this layered system. LIDAR data, when combined with thermal sensors and spectroscopy, helps scientists estimate carbon storage, track forest health, and monitor changes over time. It can even reveal which areas are thriving and which are struggling under the pressures of logging and climate change. In essence, the forest is learning to speak in numbers, and we're learning to listen. Still, there are things technology cannot yet describe. The shimmer of fog in morning light, the quiet resilience of a bromeliad holding a pool of rainwater, and the tiny world inside it. The canopy is full of these miniature ecosystems, small ponds in leaves that host entire food webs, vines that bridge trees like living highways, ants that farm fungi in their nests. Every cubic meter holds secrets. Mapping can only show the outlines. The stories still belong to biology, patience, and imagination. Cloud forests perched on tropical mountains add another layer of complexity. Here, cool air rises from the valleys, condenses into mist, and lingers like breath over the ridges. These forests are perpetually damp, wrapped in clouds for much of the day. The constant moisture gives them their characteristic mossy texture, branches thick with ferns, bark hidden beneath carpets of green. It also makes them crucial water sources. The trees capture fog from the air, creating a gentle rain that feeds streams even in dry seasons. Entire cities downstream depend on this invisible harvest. But climate change is pushing the clouds higher. In many regions, the mist now forms at greater altitudes, leaving the lower forests drier and more vulnerable. Scientists can see this shift from space, the spectral signature of the canopy subtly changing as humidity drops and species migrate uphill in search of moisture. The forest is, quite literally, climbing the mountains. Mapping these trends helps conservationists identify which areas need protection most urgently, because once the clouds rise beyond the peaks, there's nowhere left for the forest to go. In a way, our attempts to chart these ecosystems are acts of humility. The canopy reminds us that Earth's geography isn't only horizontal, it's vertical too, stacked in layers, each one a distinct landscape. The challenge isn't just to measure space, but to appreciate depth. The sky-tinted roof, the mid-level corridors, the dim floor below where roots and fungi weave their own networks. Every forest is a kind of inverted city, alive from the ground up and the air down. Yet for all the data, maps, and models, nothing compares to standing within it. To see sunlight scattered through fog, to feel the damp air thicken with the scent of orchids, is to sense how alive the world can be. Up there, among the branches, geography becomes something tactile. A geography of touch and breath, measured not in kilometres, but in textures and sounds. The story of mapping the canopy is really the story of finding clarity in chaos. From satellites peering through clouds to lasers painting invisible patterns across leaves, we're slowly revealing the structure of what was once unknowable. But the beauty of it all is that even with every new discovery, the forest keeps a few secrets. It remains, in essence, a moving mystery, a reminder that not all frontiers lie in the distance. Some hang quietly just above our heads, veiled in mist and dripping softly into the world below. And as the green world hums beneath the fog, its endless whispers give way to another kind of landscape entirely, one where the colours fade from emerald to gold and the air dries into stillness. From this symphony of moisture and leaves, the earth turns once more towards silence, where dunes, not trees, shape the horizon. There are few things on earth that seem as permanent as sand. It stretches endlessly across deserts, ancient and unmoving, or so it appears. But sand, for all its stillness, is a wanderer. Each grain, lifted and carried by the wind, joins a slow, silent migration that reshapes the land over time. Dunes march, rivers vanish, and coastlines drift. It's a geography written not in ink, but in motion. To understand this restless world, it helps to know a simple truth. The Earth's surface is never truly still. Wind, water, and gravity are always rearranging it, grain by grain. Deserts, often imagined as barren and empty, are among the most dynamic landscapes on the planet. Their dunes move like waves, slow, graceful, and relentless. What looks like permanence is really an ongoing journey. The physics of dune migration begins with wind. When air flows over the ground, it picks up tiny particles of sand, bouncing them along the surface in a process called saltation. Each grain that lands knocks others loose, creating a chain reaction of movement. Over time, this constant hopping and tumbling builds dunes, vast sculpted forms shaped by the prevailing winds. Where the wind blows steadily from one direction, dunes form classic crescent shapes known as barchans. Their gentle windward slopes face the breeze, while their steep slip faces trail behind, marking the direction of travel. These dunes are not static sculptures. A bachan can move several meters in a year, and smaller ones even faster. They travel like slow animals, each one keeping its shape while sliding across the desert floor. Satellite images taken over decades reveal their migration clearly, a graceful procession of sandhills creeping across the landscape. In some regions, entire dune fields have advanced into farmland or roads, swallowing villages and forcing people to relocate. The Sahara, the Arabian Peninsula, and parts of Central Asia are full of such stories, where the desert behaves less like a place and more like a tide. Different winds create different dunes. In regions where breezes shift direction seasonally, the dunes grow complex. Star dunes with multiple arms radiating from a central peak, or linear dunes that stretch for hundreds of kilometers like parallel brushstrokes. Between them lie interdune corridors, long flat areas where water occasionally pools after rare rains. These corridors can vanish and reappear depending on the season, creating a rhythm of absence and return that gives the desert its strange sense of pulse. The study of these changes is a modern form of cartographic patience. Using remote sensing satellites, scientists track dune movements year after year, comparing time series of images to see how the land shifts. The changes are slow enough to escape daily notice, yet fast enough to redraw maps within a human lifetime. In Namibia, for example, dunes in the Namib Desert move about 10 to 15 meters annually. In China's Taklamakan Desert, windstorms can shift entire sand ridges overnight. It's like watching the land breathe, inhaling and exhaling with the weather. Sand doesn't only reshape deserts, it builds coasts too. Along shorelines, waves and wind interact to move sandbars and beaches in endless cycles. Barrier islands migrate landward as sea levels rise, while river deltas expand or retreat depending on the balance between sediment supply and erosion. The Mississippi Delta, the Nile Delta, and the Ganges-Brahmaputra Delta are all landscapes in motion, their outlines constantly rewritten by floods and tides. Cartographers call these ephemeral lands, because even as you map them, they begin to change. Some of the most dramatic transformations occur when rivers themselves decide to wander. Over time, the accumulation of sediment can force a river to abandon its old channel and carve a new one, a process known as avulsion. The result is a shifting maze of abandoned meanders, oxbow lakes, and newly born streams. On satellite maps, these appear as tangled ribbons of blue and green, evidence of a landscape that never settles. The Brahmaputra River in India, for instance, has moved tens of kilometers across its floodplain within just a few centuries. For local communities, the geography of home must be as flexible as the river's will. Even deserts, often seen as timeless, can host rivers, though not the kind that last. In the world's driest regions, such as the Sahara or the Atacama, ephemeral rivers flow only after rare storms, racing briefly across the sand before vanishing into the ground. From space, their channels look like silver veins, reminders of wetter ages long past. These dry rivers record the desert's memory of water, hinting at ancient climates when rain was plentiful and the dunes were still sleeping. Mapping such fleeting features requires a different philosophy of geography. Traditional maps, with their fixed boundaries and solid lines, struggle to capture landscapes that move. How do you draw something that won't stay still? Satellite imagery helps, of course, but even digital maps must choose a moment in time, a snapshot of a shape that might already be gone. Cartographers who study these regions often speak of living maps, where movement itself becomes the feature. Instead of static borders, the map shows probabilities, trends and flows, an honest portrait of a changing planet. And change, it turns out, is the one constant. The forces that shift dunes and rivers are the same, that sculpted continents over millions of years. Wind and water are patient artists, capable of both destruction and creation. In the Rub al-Khali, the empty quarter of Arabia, Winds have built dunes up to 250 meters high, their crests so vast they resemble mountain ranges from afar. In the deserts of Peru, some dunes are so ancient that their shapes have fossilized, preserved under layers of newer sand like geological palimpsests. The landscape keeps rewriting itself on the same parchment. For those who live amid this movement, adaptation is everything. Nomadic herders in Africa's Sahel know the moods of the dunes better than any satellite. They read subtle cues in the sand, the grain size the winds whisper, the way a dune casts its shadow, to decide where to travel next. In coastal regions, entire communities build flexible architecture, shifting with the shoreline rather than fighting it. Humanity, in a sense, is learning from the desert, to move when the map moves. The fascination with dunes isn't just scientific, it's deeply aesthetic. From above, their shapes look like waves frozen in time, their sinuous lines glowing gold and bronze in low sunlight. Each ripple marks a conversation between wind and sand, a dialogue as old as the planet. To walk among them is to feel scale dissolve, horizons blur, distances deceive, and sound softens until only the wind remains. In the right light, even the shadows seem to drift. And despite the dryness, deserts are far from dead. Beneath the surface, moisture lingers. Seeds wait patiently for rain that may not come for years. When it does, the transformation is immediate. Flowers bloom, insects rise, and ephemeral lakes appear where dunes had slept. For a few fleeting weeks, the desert turns green, as if reminding the earth that even the most transient landscapes hold life in reserve. In the end, the movement of sand and rivers teaches a quiet lesson about the nature of geography itself. The lines we draw, coastlines, rivers, dunes, are temporary. Maps are moments, not monuments. They capture the world mid-motion, freezing a gesture that will soon change. To understand a landscape like this is to accept impermanence, to see beauty not in stability but in flow. The dunes keep shifting, the rivers keep wandering, and the mapmakers keep chasing both, knowing they will never catch them. Because just beyond every measured line, the wind is already at work, sculpting a new horizon. And as the sands continue their slow migration, the edges of the land blur once again, an endless dance of movement, a quiet rebellion against the idea of fixed borders, waiting for the next gust to draw the world anew. For all our efforts to draw neat lines on maps, nature has never been particularly cooperative. We like to imagine borders as static, solid black lines separating one place from another, but the earth quietly ignores them. Rivers wander, glaciers retreat, and coastlines breathe in and out with the tides. The planet is always moving, redrawing its own boundaries, and sometimes it takes the lawyers a few decades to catch up. Among all the ways that borders shift, rivers are perhaps the most mischievous. They look reliable on a map, graceful curves dividing one land from another, but in reality, they are among the most restless features on Earth. A river's job is to flow, and in doing so, it erodes its banks, deposits sediment, and occasionally decides to meander in an entirely new direction. In legal terms, this creates a quiet headache known as the doctrine of accretion and avulsion. Accretion is the gentle process by which land slowly builds up or erodes away as a river changes course over time. If the change is gradual, the boundary moves with it. The law, like the water, flows along peacefully. But avulsion, the sudden dramatic shift of a river's channel after a flood or earthquake, is another story. When that happens, the boundary is supposed to stay where the river used to be. In other words, if the river decides to leap sideways overnight, the map pretends it didn't. Of course, nature rarely files the proper paperwork, and so confusion follows. It's a perfect example of how humans try to impose permanence on something inherently fluid. We can survey, legislate, and even fence a border, But when the river itself is the border, the situation becomes, well, liquid. As one geographer put it, sometimes the river votes with its feet. Rivers have been redrawing maps since the beginning of time. Even without the intervention of floods, their channels migrate steadily. The Mississippi River, for example, has changed its course dozens of times over the past few thousand years, leaving behind a necklace of oxbow lakes and abandoned meanders. The same happens across Asia, Africa, and Europe, wherever sediment-rich rivers snake across wide floodplains. If you could watch them in time-lapse from above, you'd see them waltz, swaying side to side, leaving scars of old channels behind. Cartographers have always struggled with this. Early maps often fixed river boundaries in ink, unaware that the line was already outdated. Modern satellite imagery helps, but even now, natural borders defy absolute accuracy. When a river marks an international line, its subtle shifts can have real consequences, land appearing or disappearing from one side or the other. In most cases, such changes are quietly accepted as nature's prerogative, but they highlight how temporary human definitions can be compared to the patience of water. The law has a few clever ideas to keep up. One is the Thalweg principle, which states that when a river marks a boundary, the dividing line follows its deepest navigable channel. It's a practical rule since that's often where ships can pass, but it introduces a delightful paradox. When the riverbed deepens unevenly, so too does the border. In effect, the frontier zigzags invisibly along the water's hidden contours, shifting with each new flood or deposit. It's like tracing a line through liquid glass. Glaciers create similar puzzles. Though they move far more slowly than rivers, their motion can still redraw the landscape dramatically. In mountainous regions, the ice carves valleys, pushes debris, and leaves behind ridges called moraines that mark its advance and retreat. When the climate warms and glaciers shrink, entire watersheds can change direction. A stream that once flowed one way may suddenly find a lower route through a newly exposed valley, shifting drainage basins, and sometimes borders, with it. Even coastlines are in constant negotiation. Tides, storms, and sea level rise are forever reshaping them. Deltas expand and retreat as sediment supply changes. Barrier islands migrate toward the land. Cliffs crumble into the waves. When boundaries are drawn along the mean high water mark, as many coastal ones are, that definition quietly moves too. Some nations have found their borders creeping landward as the sea claims new ground. The map, as always, trails behind reality. The problem, of course, is that human institutions crave stability. Borders exist so we can agree on where one jurisdiction ends and another begins, but the Earth doesn't recognize such agreements. It just does what gravity, weather, and time dictate. The result is a fascinating intersection of law and geology, a conversation between parchment and planet. There's also a philosophical side to it. Moving borders remind us that the very idea of ownership over land is a kind of illusion. We mark territory, build fences and plant flags, yet the ground beneath our feet is constantly changing. The Himalayas are still rising, the Great Rift Valley is still widening, and coastlines are always on the move. From a geological perspective, the entire planet is a work in progress. This constant motion has practical implications too. Remote sensing has allowed scientists to track changes in natural boundaries in extraordinary detail. Time series imagery shows rivers shifting course, glaciers thinning, and coastlines receding year by year. Governments use this data to update boundaries, manage resources, and anticipate environmental change. It's cartography as real-time storytelling, where each frame reveals how the planet edits itself. Even deserts, seemingly featureless, participate in this dance. Dune fields migrate with the wind, and dry riverbeds, called wadis or arroyos, fill with water during rare storms, carving new paths through the sand. In high latitudes, permafrost melt can redirect entire drainage systems, and in polar regions, the melting of ice shelves reveals new coastlines, while floating sea ice continues its seasonal ballet across the poles. The line between land and sea, between ice and ocean, shifts daily. Viewed this way, borders become less like walls and more like currents, fluid lines that reflect the ongoing conversation between Earth's forces. Humans simply trace these movements and call them agreements. A treaty might define a boundary by latitude and longitude, but on the ground the land rarely obeys so neatly. Mountains erode, rivers wander, and glaciers retreat. The ink, no matter how permanent, always fades. Yet there's beauty in this impermanence. Moving borders invite us to see the world not as divided spaces, but as overlapping zones of change. They remind us that the environment is alive, that even the hardest stone eventually flows given enough time. The ground is not a stage but a participant in its own story. Sometimes, when rivers abandon their old beds or glaciers reveal new valleys, they uncover histories buried beneath. Fossils, sediments, traces of past climates. The shifting of borders doesn't just rearrange geography, it uncovers memory. The Earth, by refusing to stay still, teaches us to pay attention. So the next time you glance at a map and see a neat blue line marking a river, imagine it whispering softly, "Not for long." The cartographer may try to fix it in place, but the current has other plans. Nature's borders are patient and unpredictable, sometimes drifting by millimeters a year, sometimes leaping in a single flood. And when the river finally decides to vote with its feet, all we can do is redraw the line and nod in quiet respect. For all our attempts at order, the world remains gloriously untidy. The borders move, the glaciers shift, and the maps politely struggle to keep up. And just beyond those restless lines lie other uncertainties. Place is not defined by change, but by absence. If moving rivers test our sense of control, blank spaces test our sense of understanding. Those too have geography, just of a different kind, shaped not by motion, but by what we still fail to see. Late at night, when the world's lights are dim and the hum of activity fades, the Earth keeps on sending signals into space. Satellites drift overhead, quietly taking its picture, measuring heat, elevation, vegetation, water, and the invisible trails of our lives. But if you could stand in a control room and watch all those glowing dots of data gathering around the globe, you'd notice something strange. Amid the bright constellations of information, cities, shipping lanes, fertile valleys, there are darker patches, vast areas of the planet that remain undermapped, undermeasured, and quietly missing. These are the data deserts, the modern world's new blank spaces. For most of history, blank maps were literal, areas explorers hadn't reached or regions deliberately left vague because no one quite knew what lay there. Today we can see almost everywhere. We can peer through clouds, sense temperature changes across forests, and measure soil moisture from orbit. And yet our global picture is far from complete. The blanks have changed shape, but they haven't disappeared. Instead of geographical unknowns, we now have data unknowns, places where the technology, the access, or the priorities fall short. Some of these gaps exist simply because of cost. Mapping is expensive. Satellites may seem like the ultimate tools of convenience, but launching them, maintaining them, and processing their data all take enormous resources. Most high-resolution imagery is collected not by governments, but by private companies, and their lenses tend to linger over places that generate demand: cities, coastlines, and infrastructure. Remote deserts, dense forests, and sparsely populated regions often get fewer updates. The economics of curiosity have a bias of their own. Then there's accessibility. In some regions, difficult terrain, cloud cover, or dense vegetation physically block our view. thick tropical canopies, like those over the Amazon or the Congo basin, swallow radar and scatter light. The forest floor beneath remains hidden, even to satellites designed to pierce the green. Clouds are another persistent obstacle, especially in equatorial zones where clear skies are rare. An area might be imaged hundreds of times a year, yet the usable pictures, those without clouds, are few and far between. The result is an incomplete mosaic, a patchwork of clarity and blur, precision and mystery. Conflict zones create another kind of data desert. In areas of political instability, aerial surveys are often restricted or impossible. Satellite images may be classified, delayed or degraded for security reasons. The result isn't just a lack of information, but a selective silence. Where data vanishes, understanding fades with it. It's an absence that echoes through research, relief work and planning. Even humanitarian efforts rely on good maps, and when those maps go blank, it's not only geography that suffers, it's people. Some gaps paradoxically arise from abundance. Urban areas are mapped to microscopic precision, updated daily or even hourly. Sensors count cars, monitor air quality, track temperature changes street by street. Meanwhile, rural regions, where billions still live, often have only coarse or outdated coverage. It's a digital form of inequality, a geography of attention shaped by where people, money and infrastructure cluster. The result is that half the world's population appears in high definition, while the other half lingers in soft focus. Even the most advanced global datasets reflect this imbalance. Elevation models are often far more detailed in Europe or North America than in Africa or parts of Asia. Land use maps can show exact field boundaries in one country and little more than green smudges in another. It's not a conspiracy, just a mirror of priorities. We map what we value, or at least what we fund. The unevenness extends into the digital age. Apps and navigation systems depend on commercial mapping databases built from user activity. The more people drive, walk, and post location data, the sharper the map becomes. In quiet rural regions, there's simply less digital noise to learn from. The result is a feedback loop. The well-mapped places keep improving, while the poorly mapped remain obscure. Even crowdsourced mapping projects like OpenStreetMap reflect this pattern. Volunteers tend to live in or focus on populated areas, leaving the world's quieter corners underrepresented. These gaps have real consequences. Incomplete data affects everything from disaster response to conservation. When an earthquake hits or a flood spreads, responders rely on accurate maps to know where roads, rivers and settlements are. If those features are missing, aid slows. In climate science, areas with sparse measurements can distort global models, leaving us less certain about how local ecosystems are responding to change. The blanks on our digital maps are not harmless, they're blind spots that shape decisions. And yet, there's also something humbling about these absences. They remind us that no technology, however advanced, can capture everything. Nature still guards some secrets. The oceans, for instance, remain patchy in data despite fleets of satellites scanning the waves. Cloud cover, light reflection, and the sheer depth of the water confound our instruments. Even with the best sonar and radar, vast areas of the seafloor remain inferred rather than seen. The same goes for remote ice sheets, deep jungles and deserts where shifting dunes erase landmarks faster than we can record them. In the quiet glow of that control room, the gaps are almost poetic, reminders that the map of Earth is still in places unfinished. But they're also reminders of bias. Every dataset reflects the values and structures of the society that created it. When we decide where to point a satellite, what to measure, and how often to update it, we're making choices that shape how we understand the planet. Consider how differently urban and rural areas appear when viewed through data. Cities glow like constellations in satellite night images, their lights traced by highways and industry. But light isn't just illumination. It's a proxy for attention. A village without electricity vanishes from that view, even though it exists. In the data, darkness often equals absence, and absence can be mistaken for insignificance. It's not that the world's quiet places matter less. They simply shine less brightly in the kinds of maps we build. The challenge is not just to fill the blanks, but to understand why they exist. Some are technical, others political or economic, and some are ethical. Should every inch of the planet be mapped in high detail? Does total visibility come at the cost of privacy or cultural respect? Indigenous territories, for example, often appear as empty spaces on official maps, even though they are rich with meaning and knowledge. The act of mapping can itself be a kind of bias, flattening lived landscapes into coordinates. In recent years, a movement toward open data has begun to close some of these gaps. Small nations and citizen scientists contribute local surveys, drones gather imagery from remote regions, and machine learning fills in missing pixels using statistical patterns. It's a remarkable effort, like collective cartography on a planetary scale. Still, the pace of improvement can't erase the fundamental truth that mapping is never neutral. Every map, even one made of data points and algorithms, is a story told from somewhere. So the next time you look at a digital globe and see its glowing grid of detail, remember that it's both a triumph and a confession. The brilliance of our technology reveals how much we've learned, but the quiet spaces between those pixels remind us of how much remains unseen. In those dim regions, the cloudy, the remote, the unprofitable, the world keeps its secrets. And as the satellites continue their slow orbits, blinking silently above us, the dark patches will shift and shrink but never entirely vanish. There will always be corners of the Earth that remain incomplete, at least for a while longer, places where data thins, where the digital light fades, and where mystery still has room to breathe. Yet, not all blank spaces are accidental. Some are deliberate, maps with their edges blurred by human choice rather than ignorance. From the quiet darkness of missing data, the story of mapping begins to move toward another kind of absence, the kind made on purpose, where the pixels dim not for lack of information, but for reasons of secrecy, safety, or discretion. Not every blank space on a map is born of ignorance. Some are made deliberately by design, policy, or quiet agreement. If you've ever zoomed in on a satellite image and found a blur where you expected detail, or a patch of low resolution surrounded by crisp clarity, you've glimpsed the geography of secrecy. These aren't the ghosts of uncharted lands. They're places intentionally veiled, where the edges of visibility are drawn not by clouds or canopies but by human choice. The impulse to conceal parts of a map is almost as old as map-making itself. Long before satellites, monarchs and merchants alike understood that information was power. Detailed charts of coastlines, fortresses, or trade routes were guarded as closely as treasure. A nation's map was a strategic asset, revealing not only its territory but its vulnerabilities. During the age of exploration, captains often doctored maps before sharing them, omitting islands or shifting coordinates to protect valuable discoveries. The art of deception was, in its way, a form of cartography too. Modern blurring serves a different purpose but follows the same logic. Security, privacy, and safety all play a role in deciding what we can and cannot see. Many governments restrict the publication of high-resolution imagery for sensitive sites such as military bases, research facilities, or energy infrastructure. In some cases, the areas are pixelated or replaced with low-detail substitutes. In others, the imagery may simply be older or lower in resolution than the surroundings. It's a subtle approach, less a blackout than a soft focus. Commercial mapping platforms also apply their own layers of discretion. They must balance accuracy with legal compliance, as every country sets its own rules about what may be shown. Some regions limit resolution across entire territories, while others specify only certain zones. The result is a patchwork of clarity, where one coastline gleams in crisp definition and another dissolves into abstraction. A trained eye can often spot these decisions, the telltale smudge where a shoreline once curved, or a city block rendered suspiciously plain compared to its neighbours. Then there are cases motivated not by national security, but by personal privacy. As aerial imagery becomes more detailed, the line between geographic data and personal exposure grows thinner. A satellite photo taken from orbit can now resolve features smaller than half a metre, enough to distinguish cars, boats and rooftops. That precision brings value to planners and scientists, but it also invites ethical questions. How visible should daily life be from above? To protect individuals, mapping companies often anonymize or generalize small-scale details, blurring house numbers, concealing private gardens, or averaging out clusters of pixels so that a location remains recognizable but not revealing. This kind of editing has a long tradition in cartography. Even in pre-digital maps, features were often simplified for readability or aesthetics. Coastlines, for example, are notoriously difficult to draw at full fidelity. Their fractal complexity, bays within bays, rocks within reefs, means that any map must generalize them. A line on paper can never match the real, wrinkled texture of land meeting sea. This process of smoothing and simplification, known as shoreline generalization, is both a practical and an artistic decision. In modern digital maps, similar algorithms are applied automatically, scaling the amount of visible detail depending on how far you zoom in. The map doesn't lie, it just tells less of the truth at once. Sometimes omission protects not people but environments. Sensitive ecological sites such as endangered species habitats or archaeological remains may be intentionally disguised to prevent disturbance or looting. Conservation agencies occasionally request that the exact coordinates of rare nesting grounds, caves or reefs be withheld from public databases. It's an unusual reversal, hiding the location of something not because it is dangerous to us but because we are dangerous to it. In such cases, secrecy becomes a form of stewardship. Even the limits of satellite resolution can act as a kind of built-in discretion. International agreements once capped how detailed publicly available imagery could be, ensuring that commercial data didn't surpass the capabilities of state-run systems. Though those limits have eased over time, many regions are still depicted at a reduced level of sharpness. To the casual viewer, it's barely noticeable, but to an analyst, it marks the boundary between what's known and what's permitted. The pixels themselves become a kind of diplomacy. In the digital age, these choices ripple outward in unexpected ways. When an area is blurred or masked, it can attract attention rather than deflect it. Online communities have made a hobby of searching for inconsistencies in satellite imagery, speculating about what lies beneath. Sometimes the answer is mundane, a data error, a cloud shadow, an outdated image. But occasionally, curiosity meets the very secrecy it seeks to uncover, creating an odd dance between transparency and obscurity. The more visible the world becomes, the more meaning we assign to what we can't quite see. From a cartographic perspective, this tension raises an important question. How much information is enough? A perfect map, one that captured every detail at every moment, would be overwhelming. An infinite mirror of reality. The beauty of maps lies in their selectivity, in what they choose to emphasize or omit. Every omission, whether by policy or by design, defines the character of the map itself. Some absences protect, others simplify, and a few simply acknowledge that total knowledge is neither possible nor desirable. Even in public datasets, intentional blur extends beyond physical features. Economic, demographic, and environmental information is often aggregated or rounded to protect privacy. Population maps use grid squares rather than exact household counts. Agricultural data may be averaged over regions. These choices guard individuals while preserving patterns. The result is a picture that's accurate in shape but soft in detail, a statistical fog that balances truth with discretion. At the heart of all this lies a delicate trade-off between openness and responsibility. The more we map, the greater our ability to act, plan, and protect. Yet the same precision that aids discovery can enable intrusion. It's a paradox that has accompanied mapping since its beginning. Visibility empowers, but it also exposes. The blur in that sense is not a flaw, it's a form of restraint, a reminder that even knowledge benefits from boundaries. From a quiet control room filled with glowing screens, these decisions unfold silently. Engineers and analysts adjust resolution thresholds, review regulations, and process endless streams of imagery. Each blurred edge or softened contour represents a choice, sometimes technical, sometimes ethical, often both. The result is a planet rendered in high definition, but wrapped in selective modesty, a world simultaneously illuminated and discreet. And though the maps grow sharper every year, there will always be places that remain hazy, not through oversight, but intention. They are the faint fingerprints of human caution in an age of total visibility. Every blur, every missing detail is a small pause in our relentless gaze, a reminder that even in the age of satellites, not everything needs to be seen. Beyond those blurred edges, though, lies something far less voluntary, the darkness of depth itself. If some parts of the map are hidden by choice, others are hidden by nature, drowned in shadow, pressure, and silence. Beyond secrecy lies the world's true abyss, the deep places that even light cannot reach. Far below the ocean's rolling surface, deeper than light can ever travel, the earth folds into itself. The seafloor descends in long, graceful arcs until it suddenly plummets into blackness. The trenches. These are the planet's deepest scars, narrow wounds where tectonic plates collide and one is forced beneath another. It's here, in the Hadal realm, named for Hades, the underworld of Greek mythology, that geography meets its ultimate limit. Trenches form at subduction zones, those restless borders where an oceanic plate slides under a continental or another oceanic plate. As it sinks, the descending slab drags the seafloor down with it, creating a long, V-shaped depression that can stretch for thousands of kilometers. The Mariana Trench in the Western Pacific is the most famous of these, plunging nearly 11,000 meters below the waves, so deep that if you dropped Mount Everest into it, the summit would still be 2 kilometers underwater. And yet, for all its enormity, the trench is only about 70 kilometers wide. The geography of the Hadal realm is defined not by vastness, but by intensity. Mapping such places is a challenge of extremes. The pressure at the bottom of the deepest trenches exceeds 1,000 times the pressure at the surface. Every square centimetre of a submersible hull must withstand a literal mountain of water pressing down on it. Electronic instruments struggle to function under such conditions. Even the smallest leak or fault can mean failure. For decades, the depths below 6,000 meters were known mostly through inference. Lines on charts drawn from sparse sonar readings and educated guesswork. The Hadal world existed more as imagination than observation. When multi-beam sonar arrived in the mid-20th century, it changed that, but only slightly. Ships could now send out broad fans of sound waves, mapping wide swaths of seafloor in detail far beyond the old single-beam echo sounders. Yet even the most advanced systems can only scan a narrow corridor beneath the ship as it moves. Considering that Earth's trenches snake across tens of thousands of kilometers, the proportion directly surveyed remains tiny. The ocean once again is winning the game of secrecy. The Mariana Trench alone has been traversed by mapping ships many times, but the coverage is still patchy, ribbons of data separated by gaps of darkness. The same is true for the Tonga, Kuril-Kamchatka, and Philippine trenches, each with its own bends and ridges, each hiding steep walls, terraces, and fault scarps that we've barely begun to chart. The result is a global atlas of the deep that looks almost like a drawing in progress. Bold outlines filled in only where our instruments have passed. And yet, in those few places we've explored closely, the detail is astonishing. The walls of the trenches aren't smooth, as early explorers imagined, but rugged and complex. Landslides tumble from their flanks, sediment fans spread out like underwater deltas, and small volcanic vents speckle the slopes. Some trenches even contain narrow ledges where sediments collect, forming oases of soft mud amid the surrounding basalt. The deepest parts, the Hadal zones, are not barren chasms but active ecosystems, shaped by the slow rain of organic material falling from above. Even here, life persists. Pressure, darkness, and cold combine to create an environment utterly unlike the rest of the planet. Sunlight fades away around 200 meters down. By 1,000 meters, it is gone entirely. The temperature hovers just above freezing, and yet the ocean here is calm. No waves, no wind, only the quiet hum of currents drifting like ghosts. The darkness feels thick, layered like velvet. Every descent into these depths is an act of both science and faith. Only a handful of humans have ever visited the deepest trenches. In 1960, the bathyscaphe Trieste made history when it descended to the bottom of the Challenger Deep, piloted by Jacques Picard and Don Walsh. They spent just 20 minutes on the seafloor, peering through a small window into a world that had never known light. Since then, a few other missions have followed, robotic and crude alike, but the total time humanity has spent in the Hadal realm could be measured in hours. Most of what we know now comes from instruments that make the journey for us. Autonomous landers and remotely operated vehicles descend through the water column carrying cameras, sensors, and samplers. They drop silently into the abyss, withstand pressures that would crush steel, and record what they can before floating back to the surface. These machines have revealed trenches as surprisingly dynamic places, shaped by earthquakes, sediment flows, and even small-scale weather systems of the deep. Internal waves, invisible to the surface, ripple along the slopes, redistributing nutrients and sediments in slow motion. The biological discoveries have been equally extraordinary. Amphipods, tiny shrimp-like creatures, thrive at depths that would kill most life on Earth. Certain species of snailfish, translucent and delicate, live happily more than 8,000 meters down, their bodies adapted to withstand immense pressure. Microbes flourish within the sediments, feeding on chemical reactions that draw energy from the minerals of the crust itself. Each new expedition brings back more evidence that life, in its stubborn creativity, can flourish in even the most forbidding corners of the planet. Still, the Hadal trenches remain among the least mapped regions of Earth. Their steep, narrow geometry makes them difficult to image with sonar, which works best over broad, flat terrain. Sound waves scatter, reflect, and sometimes vanish into sidewalls, producing shadows and distortions in the data. To build a high-resolution model of a trench requires meticulous repetition, ship after ship running parallel tracks across the same feature from slightly different angles, each pass adding another thread to the picture. It is a task as time-consuming as it is mesmerizing. The result, when seen on a computer screen, resembles a digital sculpture, sharp ridges and plunging slopes rendered in shades of blue. But even that picture hides more than it shows. For every trench mapped in detail, dozens remain little more than contours on a globe. Their names, Kermadec, Java, Aleutian, evoke distant power, but their true shapes remain largely guesses. The ocean's deepest geography is still mostly rumour, wrapped in darkness. And yet, for scientists, these places hold enormous value. Trenches are key sites in the grand machinery of plate tectonics. They mark where crust disappears back into the mantle, driving earthquakes, volcanoes, and the slow renewal of the planet's surface. The sediments trapped in their depths record millions of years of geological history layer upon layer. Understanding their shape and composition helps us understand not only the sea but the solid earth beneath it. Every new measurement is a tiny step toward reading the ocean's deepest handwriting. There's a quiet irony in the fact that the most dramatic landscapes on Earth are the least visible. Mountains we can see, trenches we can only imagine through data. Their very existence is inferred from echoes, gravity, and magnetic anomalies. When ships pass overhead, their sonar pings descend into the dark and return as faint signals, each one marking a single point on a map that may take years to complete. In the Hadal realm, geography is not drawn, it's listened for. It's tempting to think of the trenches as lifeless or final, but in truth, they're among the most active parts of the planet. Continents are born from their slow recycling of crust. Earthquakes ripple outward from their hidden depths. They are not the planet's graveyards, but its engines, quietly driving the renewal of the surface we stand on. The deep may be silent, but it is never still. And so, while satellites trace the world's mountains in sharp relief and drones map the coasts in vivid colour, the deepest places remain blue mysteries, half seen and half heard. To map them fully would take centuries, yet the effort continues. Ping by ping, ship by ship, echo by echo. Every new line of data brightens the dark just a little more. For now, the trenches remain what they have always been, the planet's hidden frontiers. They remind us that the limits of geography aren't set by distance, but by depth. And as instruments tick softly in the dark and echoes return from the unseen floor, we move from the grand scale of the deepest points towards something far smaller, but no less extraordinary. The microscopic worlds that thrive within the details of that immense, uncharted sea. Along the shimmering line where land meets sea, geography becomes a living conversation. Waves arrive, tides retreat, and the boundary between water and earth redraws itself again and again. To stand at a shoreline is to witness a map in motion. Each grain of sand, each curl of surf, part of a ceaseless exchange between the solid and the fluid. For scientists, this shifting frontier is one of the hardest to pin down. It demands not just maps, but micro-maps, precise, ever-changing portraits of a planet that refuses to stay still. At first glance, a coastline looks stable. It's the reassuring edge of the world, neatly outlined on atlases with bold blue borders. But look closer. Zoom in far enough, and that line begins to waver. The shore is not a boundary, but a zone, a dance between sediment, water, wind, and life. Its shape depends on an invisible economy known as the sediment budget, the balance between what is added and what is taken away. Rivers bring silt from mountains, waves grind rock into sand, and currents carry it all along the coast. When deposits outpace erosion, the land grows. When erosion wins, the sea advances. The map never rests. Deltas are the great accountants of this exchange. They are the handwriting of rivers where they meet the sea, spreading into branching fingers and fans. The Nile, the Mississippi, and the Mekong all form vast patchworks of wetlands, channels, and shifting bars. These are places of extraordinary fertility, built from silt delivered grain by grain. Yet they're also fragile. A single flood, a dam upstream, or a storm surge can rearrange them overnight. Satellite imagery has revealed just how lively these systems are. Channels migrating, islands appearing, new inlets slicing through the mud. Even the most sophisticated maps need constant revision to keep pace. Reefs, too, are cartographic shapeshifters, though their changes are measured not just in tides, but in the growth and decline of life itself. Coral reefs form intricate three-dimensional landscapes, full of ridges, pinnacles, and labyrinthine crevices. Scientists call this quality rugosity, a measure of how rough or complex the surface is. The greater the rugosity, the greater the diversity of creatures that can find shelter and thrive. In essence, a reef's geometry is its ecology. But this living topography is under stress. Rising sea temperatures, acidifying waters, and stronger storms are reshaping coral structures faster than they can recover. Mapping them has become an urgent race against time, as divers and drones use lasers and photogrammetry to record details measured in millimeters before they are lost. Along sandy coasts, movement is more obvious but no less complex. Beaches are dynamic systems, constantly built and rebuilt by waves. Each storm leaves a signature, sculpting dunes, cutting inlets, or depositing new bars offshore. After a hurricane, aerial surveys can reveal kilometers of coastline rearranged in a single night. What was once land becomes sea. What was once a lagoon becomes a sand spit. To track such changes, scientists use time series mapping, satellite images layered across years, showing coastlines breathing in and out like a living lung. It's a reminder that even without catastrophe, motion is the norm. Sea level rise is adding a slower, steadier kind of pressure. The average increase, measured in millimeters per year, may sound modest, but over decades it reshapes entire nations. Low-lying islands and deltas are especially vulnerable, their margins thinning as water infiltrates further inland. Mangrove forests and salt marshes act as buffers, trapping sediment and softening waves. But when the sea rises faster than sediment can accumulate, even these defences retreat. The maps of tomorrow's coasts are already being drawn, not by cartographers, but by physics. Technology now allows us to see these transformations in exquisite detail. Drones skim above estuaries, capturing high-resolution imagery that can detect the tiniest shifts in dunes or reefs. Satellites equipped with radar can measure elevation changes smaller than a centimetre. LIDAR, the laser-based cousin of radar, can map underwater terrain through shallow, clear water, revealing sandbanks and coral heads once hidden. Together, these tools form a kind of planetary time-lapse, every shoreline, every reef, every tidal flat documented as it evolves. But the story they tell isn't just one of erosion or loss. Some places are gaining ground. Where rivers are still free to flow and sediment remains plentiful, new land is forming. The Ganges-Brahmaputra Delta adds islands and shoals each year. Parts of Alaska's glacial coastlines are expanding as retreating ice releases enormous amounts of sediment. Even corals, given the right conditions, can build upward fast enough to match modest sea level rise. Geography, it seems, has its own quiet resilience. Still, the balance is delicate. Human intervention often tips the scales. Building seawalls, dredging harbours, and extracting sand from beaches interrupt natural sediment flows, sometimes worsening erosion downstream. The hard edges we impose, concrete embankments or straightened channels, may protect one stretch of coast while starving another. What looks like stability on one map becomes fragility on another. The ocean, patient and persistent, eventually reclaims what rigidity denies it. Reefs and deltas share a strange kinship in this cycle of creation and loss. Both are built from fragile materials, carbonate skeletons or river silt, and both depend on continuous renewal. In deltas, that renewal comes from upstream. In reefs, it comes from life itself. When the flow of either is interrupted, the system falters. Mapping these environments helps scientists see the warning signs: shrinking mudflats, reduced sediment supply, coral skeletons bleached white by stress. The fine detail of a map becomes a form of diagnosis, a measure of planetary health. In recent years, researchers have begun merging satellite data with ocean models to predict how coastlines will look decades from now. These aren't static forecasts, but dynamic simulations, showing the shoreline migrating like a living thing. They account for currents, tides, vegetation, and human infrastructure, layering probability upon probability. The goal isn't to draw a single definitive map, but to understand the range of possibilities, the geography of the near future. And yet, for all the science, there remains something poetic about coasts. They are the planet's conversation zone, where the language of water meets the grammar of rock. Every ripple, every shifting sandbar, every growing coral polyp contributes a line to that dialogue. Even when storms erase what seemed familiar, the shoreline's story continues, rewritten but not silenced. In the quiet after a storm, when the waves subside and the air smells of salt and renewal, you can almost sense the earth exhaling. The dunes have shifted, the reefs have rearranged, and the deltas have redrawn themselves. The cartographer's task is endless yet strangely hopeful. The world's edges are alive, restless, adaptive, ever-changing. The micromaps of our coasts remind us that geography isn't just about continents and oceans. It's about motion at every scale. A grain of sand sliding in the surf, a coral branch reaching for light, a river mouth splitting in two, all are acts of continual redrawing. Together they compose the intricate border between land and sea, where the earth sketches, erases and sketches again. And from these small natural revisions comes a sobering truth. Not all redrawing is gentle. Beyond the slow pulse of tides and the graceful curve of sediment lies another force entirely, one that edits the map not with patience but with violence. From nature's redraftings, the story now turns to catastrophe's edits, where sudden events reshape the world in a single, unforgettable stroke. Every so often, the earth takes up its pen and redraws the map in a single motion. The lines we thought permanent, rivers, shorelines, mountain slopes, shift in hours rather than centuries. It's a reminder that the planet's surface is not fixed but breathing, and sometimes that breath becomes a sigh or a roar. These moments, though devastating for those who live through them, are also part of the planet's long, slow art of renewal. The geography we inherit is often written by such sudden edits. Earthquakes are perhaps the most dramatic of these revisions. Deep underground, tectonic plates lock together under strain until the pressure becomes too much. When they finally slip, the land above jolts, sometimes rising or sinking by meters in an instant. Vertical land motion of this kind can lift coastlines or drown them, creating new bays or beaches overnight. Satellite radar can detect these changes almost immediately, revealing entire regions subtly tilted or warped. In some places, harbours suddenly find themselves stranded above the tide. In others, seawater floods fields that were dry the day before. Geography moves, and the maps follow after, quietly adjusting their contours. Volcanic eruptions add another kind of punctuation to the planet's story. Beneath the crust, molten rock presses upward, searching for a release. When it reaches the surface, it can pour across the land or explode into the sky, reshaping landscapes on a scale both terrifying and creative. Lava builds new islands and ridges, while ash settles into fertile plains. From space, these transformations are unmistakable. The sudden dark smear of fresh basalt, the expanding outline of a delta born from fire. In time, these new surfaces weather, crack, and host life again. What begins as destruction becomes, in geological time, construction. The planet's handwriting is fierce, but it is always legible. Sometimes the changes are less fiery, but no less profound. Landslides can rearrange entire valleys in seconds, especially where rain, earthquakes, or human activity loosen steep terrain. A hillside that stood for millennia can suddenly collapse, damming rivers or forming temporary lakes. These natural dams often burst later, releasing floods that carve new channels downstream. The terrain after such events is both raw and intricate, freshly scoured slopes beside hummocks of displaced earth. For geologists, each scar is a page of evidence, telling how gravity and water conspired to redraw the surface. Floods themselves are among the most frequent mapmakers. When rivers overflow, they remind us that their courses are suggestions, not promises. Sediment-laden water spreads across floodplains, depositing new layers of soil and sometimes altering the channel entirely. In extreme cases, the river abandons its old bed altogether, a process called avulsion, and cuts a new route across the land. The result is a landscape of oxbow lakes, abandoned meanders, and fertile new ground. Satellite imagery after such floods reveals the artistry of chaos, swirling patterns of mud and silt, the earth repainting its own edges. Even the sea participates in this restless redrawing. Tsunamis, born from undersea quakes or landslides, can rearrange entire coastlines. Their waves move faster than a jet aircraft, but when they reach shallow water, they slow and rise, turning invisible energy into tangible shape. The water that surges ashore carries not just force, but sediment, scouring beaches, flattening dunes, and redistributing the shore. Afterward, aerial surveys often show a coastline subtly redefined. What was once a line of vegetation becomes bare sand. Lagoons merge or separate. Estuaries shift their mouths. Though such changes bring immense loss, they also reveal the deep interconnectedness of land and sea, the delicate balance of energy that constantly reshapes both. In the aftermath of these events, mapping becomes an act of both science and healing. Satellites orbit silently above the chaos, capturing images that help responders understand what has changed. Before and after comparisons show more than damage, they show the Earth's new geometry. Roads twist where the ground has lifted, rivers cut through fresh breaches, volcanic cones alter their slopes. Every pixel of these maps carries both data and emotion, the visual echo of a world that has moved. Sometimes the transformations are quietly creative. In the ocean, volcanic eruptions can build new islands from nothing, steaming into existence as the lava cools. Some vanish within months, eroded by waves. Others persist, developing beaches, vegetation, even nesting birds. These ephemeral islands are the planet's fleeting sketches, drawn in molten ink. Each one is a reminder that the world's outlines are still in draft form, constantly edited by unseen forces. Even glaciers, which seem the embodiment of stillness, reshape maps through motion. Their slow advance carves valleys. Their retreat reveals new lakes and ridges. When ice melts suddenly, enormous floods called Gjökullaups burst from beneath, scouring the landscape clean. The shifting weight of glaciers can even cause the land beneath to rebound upward, changing coastlines long after the ice has gone. What appears frozen is, in truth, a kind of liquid in slow motion. These sudden or subtle events remind us that the idea of a finished Earth is an illusion. The crust is elastic, the seas are mobile, and the atmosphere is always at work. Every earthquake or eruption is a reminder of how thin the boundary is between stability and change. We build cities, plant fields, and draw borders, all the while resting on ground that quietly rearranges itself beneath us. The planet doesn't erase, it revises. Yet amid the destruction, there's often renewal. The ash from eruptions becomes fertile soil. Floods replenish the plains they devastate. Landslides expose minerals and create habitats for new ecosystems. Even the most violent shifts contribute to the planet's resilience. The Earth is not fragile so much as fluid, its balance maintained by movement. Technology allows us to witness these changes with unprecedented clarity. Space-based radar can detect ground deformation, measured in millimeters. Drones capture the shifting outlines of rivers and deltas within days. Scientists overlay digital elevation models, comparing them year by year to see how the world reshapes itself. The precision of this monitoring turns catastrophe into knowledge, tragedy into data that can help predict and mitigate the next event. There is a quiet grace to this perspective. To watch a volcano form a new island or a river carve a new channel is to glimpse the Earth's creative process in real time. It's humbling to realize that the same forces that destroy are also those that built every mountain, island and plain. The planet's language is motion, and every upheaval is a sentence in its ongoing story. But these changes are not only geological, they're deeply human. When landscapes shift, so do lives. Communities adapt, rebuild, and reimagine their place within the new terrain. Mapping after disaster becomes an act of recovery, a way of restoring orientation when the familiar has vanished. To redraw the map is to reassert belonging, to say, here is where we are again. In the end, what's most remarkable is how the Earth continues to surprise us. We often think of change as gradual, measured in ages and eons, but sometimes it comes as a sudden reminder that we live on a living planet. Every fault line, every volcano, every floodplain is a promise of transformation. The maps we draw are simply pauses in the process, a snapshot of a world between edits. And as those edits unfold, one by one, another kind of mapping rises quietly from below, not from satellites or seismographs, but from people. When official charts falter in the aftermath of change, countless individuals step in with phones, cameras and coordinates, illuminating the darkness pixel by pixel. From the shock of sudden change, the story now turns toward the slow, collective glow of human curiosity, the crowdsourced light that helps the planet see itself anew. Not all maps begin in laboratories or government offices. Some start in notebooks, in smartphones, or in the quiet hands of people walking their own streets. Across the world, an invisible network of volunteers is quietly redrawing the planet. One coordinate, one footpath, one rooftop at a time. This is the era of citizen mapping, where geography is no longer just a profession, but a shared act of care. The idea is simple yet revolutionary. Anyone, anywhere, can help complete the world's map. Using basic GPS tools, open platforms, and local knowledge, citizens have become the new cartographers. Their mission isn't grand conquest or discovery. It's accuracy, inclusion, and connection. These modern mappers are the quiet army of geography. Teachers, students, cyclists, farmers, coders, and dreamers, all marking the details that satellites sometimes miss. The power of this approach lies in what's known as ground truthing, checking what the data says against what the Earth actually shows. A satellite might see a blur of grey where a new neighbourhood has sprung up, but only a person on the ground can say, here is a school, here is a clinic, here is the road that floods every year. That human correction transforms the abstract into the lived. It bridges the gap between the map and the world. In places where official surveys are slow or outdated, citizen mappers fill the void. They use handheld GPS devices or even simple smartphones to log coordinates and trace routes. Sometimes the process is wonderfully low-tech. In regions with poor internet, volunteers print field papers, gridded maps they can mark by hand while walking through towns or fields. Later, those notes are scanned, uploaded and digitized into shared mapping systems. The result is a living atlas of the present, constantly updated and enriched by local eyes. Perhaps the most famous example of this movement is OpenStreetMap, an open-source platform that has grown into one of the most detailed and dynamic maps on Earth. Unlike commercial databases, it's built entirely by volunteers who add everything from highways to hiking trails, shops to streams. Its beauty lies not just in its openness, but in its adaptability. When disasters strike, an earthquake, a flood, a typhoon, thousands of contributors can map affected areas in hours, helping responders navigate roads that didn't exist on official charts. Many hands make light, layers. During humanitarian crises, this global collaboration can save lives. When an earthquake devastated parts of Haiti in 2010, digital volunteers from around the world came together to trace roads, buildings, and refugee camps from satellite imagery. The updated maps were sent directly to emergency teams on the ground, guiding ambulances and aid deliveries through shattered streets. It was a turning point for open mapping, a moment when collective effort proved faster than bureaucracy and more adaptable than any single institution. But citizen mapping isn't only about crisis. It's also about visibility, about ensuring that every community, no matter how small or remote, appears on the world's canvas. In some regions, entire villages have gone unnamed on official maps for decades. Local mappers are changing that, documenting paths, wells, schools, and landmarks with precision born of familiarity. For them, mapping is a form of recognition, a way of saying, we exist. We are here. In parts of Africa, Asia, and South America, community mapping projects have become tools for empowerment. Farmers map soil types and irrigation channels. Indigenous groups record sacred sites and ancestral trails. Residents of informal settlements trace their homes to advocate for services. What might seem like a digital hobby elsewhere becomes in these contexts a statement of presence and identity. Geography becomes democratic, a shared responsibility rather than a distant authority. The technology, though evolving rapidly, remains refreshingly accessible. Smartphones with built-in GPS can capture coordinates accurate enough for most mapping tasks. Simple apps let users tag points of interest, add notes, or photograph landmarks. Even SMS-based systems have emerged in areas with limited connectivity, allowing people to text in data that later feeds into mapping software. It's grassroots cartography powered by everyday tools, blurring the boundary between mapper and mapped. And there's something deeply human about this movement. While satellites sweep the planet in silence, citizen mappers move through it slowly, feeling its contours underfoot. They hear the rustle of leaves, the bark of dogs, the hum of local life. They record the things machines can't. What a road smells like after rain, how far a bridge feels when carrying groceries, where a community gathers when the power fails. Every annotation carries a touch of lived reality. Citizen mapping is also reshaping science. Researchers now use these open data sets to study everything from urban growth to public health. Epidemiologists trace disease outbreaks using maps updated by local contributors. Conservationists monitor deforestation and wetland changes with data supplied by park rangers and volunteers. The flow of information has reversed direction. Rather than scientists informing the public informs science. In this way, the quiet army of mappers has become part of the planet's nervous system, a network of observers extending from megacities to mountain villages. Their collective effort gives the world texture and empathy. Where once there were blank spaces, there are now stories. Of course, this work comes with challenges. Data quality varies, coverage is uneven, and enthusiasm can fade when recognition is slow to follow. Some areas are mapped in exuberant detail, while others still wait in shadow. Yet the imperfections are part of the beauty. Every open map is a work in progress, shaped by countless hands rather than dictated from above. It reflects not authority but community, a cartography of participation. And perhaps that's the quiet revolution here. The idea that the planet can be known not just from orbit but from below, from people walking through markets, paddling along rivers, or tracing the edges of their own fields. The world becomes clearer not through one grand survey, but through millions of small observations shared freely. What began as hobbyist mapping has grown into something global in scope. Today, international coalitions coordinate open mapping projects to support climate adaptation, disaster preparedness, and sustainable development. Volunteers partner with governments and researchers to fill in gaps where no data existed before. The maps they create are more than tools, they're acts of trust, woven together by a sense of shared stewardship for the planet. There's a quiet poetry in that image. Satellites humming high above and below, countless pairs of hands holding phones, pens, or GPS receivers, each marking a point that says, "This matters." Geography, once the preserve of experts, has become a kind of collective authorship, and with every update, every new street traced or river corrected, our understanding of the world becomes a little more complete and a little more human. From these local efforts rises a broader ambition to weave all these fragments into a single, living picture of the Earth, an open atlas that belongs to everyone. The Quiet Army has shown what's possible. Now the challenge grows global. From villages and valleys to entire continents, the next frontier of mapping lies in connecting the dots across the whole planet, drawing not just where things are, but how they fit together. Even now, in an age of satellites and sensors, the majority of our planet remains unmapped in detail. About 80% of the seafloor still lies beyond the reach of high-resolution data. Beneath the waves, the Earth's contours blur into suggestion. Valleys hinted at by gravity, ridges sketched by sonar tracks that are few and far between. Yet this unfinished picture isn't a failure. It's a promise, a reminder that discovery isn't over, that mystery still has geography, and that curiosity still has room to grow. The modern frontier of mapping is not about finding new continents or lost islands. It's about precision, depth, and the courage to keep exploring. The oceans, the poles, the thick canopies of forests, and the caves beneath them all remain vast territories of the unknown. Each demands its own tools, its own kind of patience, and its own blend of human and machine. At sea, the great mapping effort continues in steady arcs. Research ships crisscross the oceans, their multi-beam sonars sending fans of sound into the dark. Each pass illuminates a narrow corridor of seabed, a stripe of clarity amid the blue. The work is slow but relentless. Every voyage adds another tile to the mosaic. Over time, these fragments merge into a picture of the ocean floor, its mountains, plains, and trenches slowly emerging from shadow. Helping in this effort are fleets of autonomous underwater vehicles, or AUVs, robotic explorers that dive far below the reach of light. Equipped with sonar and cameras, they sweep over ridges and chasms, returning data of astonishing detail. Some can operate for days without human control, gliding silently through darkness guided only by inertial sensors and careful programming. Their work is quiet but transformative. Where once we guessed, now we begin to see. Drones too have joined the mapping chorus, bridging air and sea. They skim the surface of remote waters, capturing readings of temperature, salinity, and current speed. paired with satellites, they create a conversation between altitudes, space looking down, surface looking up. The combination reveals the subtle texture of the ocean's skin, showing where deep ridges tug at the waves, where cold upwellings meet warm flows, and where the hidden shape of the seabed influences everything above it. Yet the sea is only one of Earth's remaining mysteries. The poles, veiled in ice and solitude, continue to defy full understanding. Beneath Antarctica and Greenland, radar sounding reveals ghostly outlines of buried mountains and valleys, while orbiting satellites measure how the ice itself rises and falls. These frozen landscapes, though motionless to the eye, shift and breathe with the seasons. The challenge is not just mapping their surface, but their base, the place where ice meets rock, where rivers of meltwater carve unseen channels, and where clues to ancient climates lie preserved. In the Arctic, sea ice itself has become a moving target for mapping. Satellites use radar and laser altimetry to measure its thickness and extent, while ships and buoys confirm the results on the ground, or rather, on the ice. The precision of these measurements helps scientists track the changing rhythm of the planet, one melt and freeze at a time. To map ice is to map impermanence, and yet, through that impermanence, we learn endurance. On land, the canopy of the world's forests hides its own secrets. Traditional aerial imagery can't see through layers of leaves, but LiDAR, light detection and ranging, can. By sending pulses of laser light through the foliage and measuring their return, scientists can reconstruct the forest's full structure, from treetop to root. This technology has revealed not only hidden ecosystems, but also traces of ancient civilizations, long-forgotten roads, terraces, and temples now re-emerging in digital form. Each laser pulse is a whisper from the past, returning across centuries. Below ground, mapping ventures where sunlight never has. Cavers and scientists use radar and laser scanners to chart underground chambers with millimeter precision. In some systems, drones adapted for confined spaces now hover through tunnels, mapping walls in 3 dimensions. The results are otherworldly, vast voids rendered in glowing digital blue, a geography of silence brought into view. These subterranean maps don't just chart space, they chart patience. Across all these frontiers, a common thread emerges: collaboration. No single nation, company or instrument can complete the map alone. The effort to chart the remaining 80% of the world's surface has become one of humanity's quietest yet grandest collective projects. Initiatives like Seabed 2030 unite research vessels, governments, and volunteers around a shared goal: to map the entire ocean floor in high resolution by the end of this decade. Thousands of data sets once scattered across archives are being stitched together into a global portrait of the deep. It's a task as poetic as it is scientific. To map is to acknowledge existence, to give shape to what was once just darkness. But the beauty of this endeavour lies not only in its results, but in its humility. Every new image reminds us that knowledge is a tide, not a destination. We're constantly moving between what's known and what's still blurred, between clarity and curiosity. Technology continues to accelerate the process. Advances in satellite radar now allow us to measure subtle gravitational anomalies that hint at undersea ridges or basins. Airborne drones survey cliffs and coastlines with centimetre accuracy. Algorithms weave together billions of data points into digital landscapes that can be explored as if you were standing there yourself. And still, after all this, the world remains half-dreamt. Perhaps that's as it should be. The unknown is not an empty space to be conquered, but a landscape to be respected. Every unmapped canyon or cloud-shrouded mountain reminds us that the world still has depth beyond our comprehension. Mystery, it turns out, isn't the opposite of knowledge, it's the atmosphere that surrounds it. When the day ends on a mapping ship, the scene is one of gentle persistence. The deck lights cast a soft glow across the waves. Instruments hum steadily below deck. Sonar pulses echo into the dark, each one a small act of faith that the sound will return, carrying the shape of something unseen. The scientists watch the data unfold, lines turning into contours, contours into meaning. The sea around them is vast and black, yet their screens shine with small islands of certainty. We are nearing a moment when most of Earth's surface will finally be measured in detail. But even when that day comes, there will still be mysteries. Beneath the seabed, within the ice, among the stars. The point of mapping has never been to end wonder, only to refine it. The blank spaces of the old maps have not vanished. They've simply moved further away, into deeper layers of understanding. And so, the last 80% is not a void, but a vow, a promise that the human impulse to explore, to comprehend and to connect will continue as long as there are shadows left to trace. Somewhere, out on a dark ocean, a ship's instruments tick softly under a sky of stars. A beam of sound descends into black water, reflects, and returns. A small light flickers on a screen, and in that moment, another piece of the world becomes known, quietly, beautifully, and still surrounded by mystery. If there's one thought to take with you into sleep, let it be this. The edges of our maps were never mistakes. They are invitations, soft thresholds where knowledge hands you a lantern and says, go as far as you wish. Every blank place, every blurred corner, every line that wanders is simply the earth reminding us that certainty is only half the story, and the other half is wonder. Tonight we walked along many of those thresholds, coasts traced by patient rum lines, rivers that politely refused to stay put, forests whose roofs hid their own secret cities, caverns that curled downward into quiet, and trenches that folded the world into velvet dark. We listened for echoes beneath ice, watched dunes breathe with the wind, and followed the slow hum of ships mapping the deep. We saw that even in an age of sensors and satellites, mystery does not vanish, it relocates. It slips beneath canopies and under waves, into data deserts and distant gravity shadows, asking not for conquest but for attention. What matters most is how we meet those edges, with care, with humility, with a willingness to admit what we do not yet know. The ocean's floor does not hurry to be seen, the ice speaks in centuries, a cave rewards patience, a river writes in loops. The world is unafraid to take its time, and it invites us to slow down with it, to measure our curiosity in breaths rather than in leaps. There is comfort in that rhythm. The unknown is not a void to fear, but a space that holds us gently. It gives the mind a place to wander without reaching for alarms. In the soft company of uncertainty, attention becomes lighter, thoughts untangle, and sleep draws nearer. The map's edges are a lullaby written in contours and silence. If your eyes are heavy now, let them be. Think of a single sonar ping sinking through dark water and returning with a small gift of shape. Think of mist caught in the arms of a cloud forest, a drip turning to a trickle to a stream. Think of a lantern held just high enough to see the next steady step. The world does not demand that you finish it. It only asks that you notice. Thank you for travelling here tonight, for trusting geography to be your path toward rest. Your presence is a quiet kindness toward yourself, toward this little community that gathers in the dark, and toward a planet that is always more than it appears. If you'd like to drift with us again, a gentle like and a soft subscribe help this calm circle find you next time. For now, the work is done, the coastlines can keep breathing, the dunes can keep walking, the ice can keep its secrets a little longer. There will be time enough for other journeys, other edges, other lanterns. You do not have to hold the whole earth in your hands. Close the atlas in your mind with a slow breath. Feel the cover fold, quiet and sure. The lines have softened, the colours have dimmed to dusk. Somewhere beyond the window, the tide is turning. The night is drawing its cool veil across the water, and the planet is exhaling. The map rolls closed with a gentle rustle. The ocean just beyond goes on breathing.